let's see here. Are we live? Alrighty. Alright, everyone. Looks like we're live. Okay, so welcome back to another stream on our Raspberry Pi 5 based robot that'll run Robot Operating System 2 with the idea of being a SLAM based robot using the ROS2 stack. So, for those of us who are just joining in, or for those of you who are just joining in, essentially what we did in the last stream was we basically came up with a list of the hardware that we need to put in the robot, and we set everything up on a breadboard to make sure that some of this stuff would work. We didn't actually read the LiDAR or anything, but or the IMU, but we set up the motors, we set up the LiDAR motor, the LiDAR drive motor. So this week, hopefully what we're going to be doing is, this week, yeah, so, hold on just a second. Okay, so, 1 second, sorry. Alrighty, so, yeah, so tonight what our goal is that we're going to try to finish the electronics and also hopefully try to finish some of the 3D modeling in order to print out the components that we'll need to mount the hardware into the robot. So, so what we've decided on hardware-wise is we're going to be using an XV11, probably should make a note of this. So we're using an old Nito XV11 LiDAR, or a LiDAR from an old XV11 robotic vacuum cleaner. Obviously there's better stuff on the market, but I had this thing available, and the other LiDARs that I have available are quite nice, so I just don't want to use them unnecessarily for this project. But we also looked at the motors, and which are these geared brushless motors to replace the stock motors in the Stinger chassis that we're using. So initially that thing came with the orange chassis in the background. Initially that thing came with brushed DC gear motors, but you know, as I said in the last stream, that chassis I've had that chassis since Christmas of 2007. So over the years the gearbox had seized up. So replaced them with these brushless motors. Actually, these are the ones we're going to be using. The ones that are currently mounted in the robot we're going to be removing, because I believe the ones in the robot are 600 RPM motors and these are 200 RPM, so the torque is 3 times higher on these ones. Take a 3D scan of yourself and print it. That way when you... Modeling. I'm a model. Atmosphere modeling. I make the atmosphere seem... Either way. So anyway, so today what we're going to be doing is basically finishing. We did the little breadboard thing, but today we're gonna put together a schematic of what the hardware in the robot's going to look like, and then we're going to be soldering things together on a proto board. And hopefully by the end of the stream, we also wrote a tiny bit of code in the last stream to spin things up and at least make the robot remote controllable. So this time what we're going to do is hopefully we'll have it buttoned up and driving around. So let's see. All right. So let's start with a program called KiCad, which is we'll just start a new project here, which is KiCad being a a open source PCB design tool. I believe it's maintained by CERN, or at least principally. So we're going to say, I'm going to call this PiBot. Let's see, PiBot board, or PiBot logic board. Call it that, and we're going to call ourselves PiBot logic board. Okay, so now I have our new schematic here, and remember that for the most part we're using a bunch of off-the-shelf components. So the motors are off the shelf. The actual motor controllers are embedded into the motors themselves. So we don't actually have to really worry about anything from a motor driver perspective. We just have to hook up the motors correctly. And then also we have to, so we also have an IMU. But that's also, again, a little PCB that we have. And we don't actually have to like solder the IMU itself down. We just use an existing proto board. We're using a Pi Pico 2, Pico 2W. We're using a LiDAR. So basically, really all of our proto board here is turning the is taking in the connection from the battery. We're going to put the voltage regulator, which we explored in the last stream. Again, it's another little module. So basically all this proto board is doing is gluing a bunch of pre-existing little dev boards that you can buy, or eval boards that you can buy on AliExpress or Amazon. Obviously, if you build it yourself, you can select some far better components. But for just this easy introduction, kind of thing, we're just going with really cheap off-the-shelf stuff. So let's get started here. So obviously, the core of our logic board is a Pi Pico. So actually, thanks to not necessarily me specifically, but me and a couple of other interested parties, we actually now have Pi Picos in KiCad. So we can just take this Pi Pico schematic element, and we have all of our parts here. And so what we're going to do, so we have this, and so we're going to define a realistically, before we get to the Pi Pico, let's kind of do things as we set them up. So we're going to start with a connector for the power. So we're going to go con one row, and then one. So this will be basically a 2-pin connector, which is going to be our little terminal block that we solder everything together on. So this will be that little blue terminal block that the battery will screw into. So apologies for the siren in the background. So on this one, we're going to say that we have one connector. This is going to be, we're going to call this the battery connector, or battery in. And we're going to say pin 1 comes off to, we'll say pin 1. We'll define another one that goes this way. And we're going to grab our power rail. And this is going to be our 12-volt rail coming in from the battery. And then we also need to define a ground. So we'll take our ground and put it there. And now we have a battery connected to our circuit. We now are going to define some pins that our voltage regulator connects to. So we'll just define, because that voltage regulator board is that one off of AliExpress. Let me pull it up here. Let's see, AliExpress, we're going to say I'm shopping for Mini Pro 5, or Mini 560 Pro for the little thing. Yeah, so basically these little modules are what we're going to be using. We have the 5-volt, or actually these are the Pro Mini 5-volt. Yeah, so we're using these. These look a little visually different than the ones we're using. But as you can see, there's 4 major connection sites for pins. And essentially, there's a battery ground, there's a high voltage ground, high voltage positive, and then there's the regulator, and then there's a low voltage ground, and then the low voltage positive output. I say low voltage, high voltage ground. They're actually just connected together inside the board, so don't worry about that. But what we're going to do is, because these are so far apart, we're just going to define these as 4 separate pins. And so let's go grab our component again, and we're just going to do these as a collection of 4 single pin connectors. And we're just going to do that. Oops, sorry, we'll just copy that, paste this. No, sorry. Copy, paste. This is going to be vreg bat plus, or vin plus. It's going to be vreg in minus. Or yeah, we'll say, sorry, we'll just not v in, we'll just say in plus, in minus. This is going to be vreg out plus, and vreg out minus. And so we will just connect these grounds together, because that is actually how they're connected internally to, that's how they're connected internally on the regulator board anyway, so it doesn't really give us anything to connect them separately. And then vreg in is going to go to, We'll come over here where it's going to be our 12-volt rail again. So these are actually connected together. We'll put we got one last one, and this will end up being our 5-volt rail. This will be our 5-volt rail. So actually, we'll just we'll put a little text label here. It's going to be called the connection site for Mini 560 Pro 5 volts. Okay. Just put that up. No. Sorry. Move this over here. Grab this little thing. Let's say we'll place that here. This is the connection site for Mini Pro 560. And then this is just our generic battery in section. All right. So now that we have our 5 volts, if you recall from the last stream, we said that we're connecting the power in on the Pico directly to the 5-volt rail, because this will actually backfeed power into our Pi Pico. Into our Raspberry Pi over the power connector. So we'll actually just, for now, I think we just ignore the VSys pin and the 3.3 volt output. We can also ignore the 3.3 volt enable because it's just on, and we're not going to have a reset switch, so this is also just ignored. The run defaults to just run the controller, and 3 volt enable defaults to enabled unless you externally ground it. So we'll just take one of these ground symbols again and come over here and define this as connected. Alrighty, analog ground is also going to be, we don't actually have to do anything with analog ground because that's connected internally to ground. Same thing with analog voltage reference. Alright, so now let's look up the pin out of the Pi Pico 2, just so we can see where all the little peripherals are. Alrighty, we got this. Just one second, let me grab the MPU 6050. Let me just turn the camera off here. And let me go grab the board. Alrighty. So I can turn the camera back on. All right. Okay, Pi Pico out. Okay. So, we now need to decide... Okay, so before we get too deep into the sensors, we're now going to define the connections for the motors. And the motors use a 5-pin connector. We'll say 5-pin connector. So if you, off-stream anyway, if you look at my little webcam, I added little 5-pin JST connectors to the motors so that we can plug them and unplug them without having to worry about anything too fancy. And actually, while we're at it, let me grab the LiDAR as well. Okay, let me find where I put this thing. Okay, there we go. Okay, so... grab the LiDAR. I'm just grabbing all these for reference so I know how to wire everything up again. So the motors. We've got, starting from pin 1, we're going to do, well actually, I'll just copy and paste this eventually. Nope, stop. So we're going to say left, or motor left. And based on how I wired these up, we can see that pin 1 is the blue one, and pin 5 is the red one. So basically the blue is the PWM in... Actually, let me look this up again, but I'm pretty sure the blue is the PWM input line. The white is the direction control. The yellow is the encoder output. And then black is ground. And then the red is the 12-volt supply for the motor. So we're going, let me just double check this. So let's look at these are JGB 37-3525 motors. It's high torque gear motor, hopefully, images, It gives me a wiring guide here. eBay. Ooh, interesting. Does that give me a wiring guide? That'd be useful. No, they don't give me a wiring guide. Okay, that's always lovely, you know. Visit Precision Mini Drives. Oh God, no, no third party save. There we go. All right, here we go. Yeah, I got it right. So blue is the PWM signal, yellow is the encoder, white is the direction control. And so another thing that we looked at in the last video or the last stream was if you remember when I unplugged the Pico but the power was still applied, the motor turned on, and that is because the motor, if the blue line is floating, the motor automatically turns on, because these are meant to be direct replacements to just standard gear motors. So the way that the control board works is it assumes that if there's no actual digital control input, then it should just act like a standard little brushed motor and turn on when there's power applied. So we actually need to stick like a small pull down, or not small, but a large value, so that there's little current going through. But we need to stick like like 100K or something pull down resistor on this PWM line, so before the Pico turns on, or before the Pico turns on, the motor stays off, and while the Pico boots up, like that. The problem is that let's say we tell the Pico to enter programming mode. Well, now it's off while it's being programmed, and the motors will just start spinning and the robot will run away. So we need to put little pull downs on this. So starting at pin 1, since so pin 1, I connected the PWM line to. So let's take this, and so we'll call this give it a label. We'll call this the motor left PWM, and we'll just give ourselves a nice long little, oops, come back, oh God, redo, edit, redo add label. Oh, sorry, we need to rotate that because we want it to connect there. We'll just draw a little over there. It's just teething issues, so there we go with that. But we also, and then we're going to do our ground connection here, 3, 4, copy our little ground label from over here. Then we're going to copy not copy, but 1, 2, 3, 4. We'll do our 12 volt rail here. And this motor left PWM, we actually want to move this, probably another one here. All right, so we now want to add our little our resistor. So we're going to say R US, R small US, just because I like the American squiggle version of the resistor more than the European just little bar. So we're going to call this 100K, and we'll just put this over here. No, it's not working. Okay. It's working fine, but I just like to keep my little circuits compact here, but it's making it hard to draw. Okay, that's fine. Okay. So now we're going to do our pull down from up here, and we'll do our, oh, that's an odd number. I also like aligning to even numbers here. So let's say that, and then come up here, 1, 2, 3, 4. Okay, so we got our pull down to keep the motor off while it's powering up, while the board's powering up. And so we'll just draw 2 more lines here. Copy left PWM, copy. This is going to be motor left direction. And this is motor left encoder. Or we'll just call it tach. Because it's non-quadrature, so we'll just call it tachometer. Or motor left. And you know what? Yeah, well, this is fine. So we've got our left motor definition, and actually we can do these a little nice. We can actually assign, we won't really do a board layout for this, but we will assign our little footprints. So we call it terminal block I think, how does this work? Connector, there's a terminal block called in KiCad here. We want a worth connector, not footprint filters, terminal. Oh, here we go, terminal block. Just want a classic, you know, terminal block. Nothing special. Yukon, CUI Mets, Fillmore, Phoenix, R&D, TE, Wago. Ooh, Wago. Those are nice. Micromate. Okay. We'll just do an old style, just a simple old style terminal block here. What does it even look like? Oh yeah, yeah. Look at that. Those are classic. Okay, so we'll use one of those. These are just going to look like standard pin headers, right? Pin header 1 vertical, or actually we want, 2.54 millimeter. We got classic. Okay. 101 vertical. Okay. Copy that. Okay. Sorry. Cancel. Do that. Footprint. Okay. This is going to be a JST 2mm connector. 2mm, I think. Yeah, here we go. And so, here we go. Yeah, board to board, 5-pin connector, that's 2.5mm. We want a 2mm, 2.0mm vertical. Yeah, that one. Okay, we want one of these. Okay. And then we're going to define the right-hand motor. Should be the same way. So this is going to be motor right, motor right, and motor right. Okay, and then change our label here to motor right. All right, cool. So we have our 2 motor connectors, which is nice. Okay. And then now, yeah, so that gives us our tachometer, our direction, our PWM, our 12 volt. Okay, cool. So, did I wire it? Oh, I got this slightly backwards, sorry. Ooh, that would have been not fun. Okay, actually, I did this backwards. I need to delete these because this is the ground, not the 5 volts, or not the 12 volts. Okay, so we actually want to define this as our ground. We'll bring this up to be our 12 volts. This smells of oopsie here. Okay, cool. There we go. Okay, so yeah, there we go. Nice. All right, so now let's set the footprint. Hand solder, we don't want that. We actually want SMD. We just want the through holes. Pi Pico common through hole. Yeah, there we go. Unspecified. Yeah, we want the through hole version because that's what we're doing. And all right, so we've got our motor pins, and now we need to define a header for our MPU 6050. And so the little labels are along the backside here for us. So let's define our MPU 6050. So if we take a connector, and we call this, I actually want con, I believe this is an 8-pin header. Yeah, so this is con 01 by 08. Perfect. And this is the MPU 6050. And all right, so pin 1 on the MPU 6050 is 5 volts. So 1, 2, 3, 4. Take this, we're going to pull our 5 volt signal. And then the next one is ground. We'll do 1, 2, 3, 4. pick a ground. All right. And so we're going to want the interrupt pin. So yeah, sorry. So the next one is SCL. So we're going to copy, so we're going to bring some lines out here. And the next one is SDA. And then the next two are the external SDA and SDL, so we don't actually care about those. And then the next one is the AD0 pin, or the address 0 pin. So if you pull address 0 to ground, basically it selects one of two addresses for the chip. And we want the default address, which is got by grounding the AD0 pin. So most of these MPU 6050 boards actually, they have a pull-down resistor internally to ground the MPU 6050, or to ground the AD0 pin on the MPU 6050. But sometimes they don't. So we're just going to put a direct connection to ground. And then we also want the interrupt pin coming off the MPU 6050 just so we get a signal. And I also believe that from our experiments on the balancing robot before, I didn't need to use external pull-up resistors, because I think this MPU 6050 board actually integrates 2.2K pull-ups, if I recall correctly, which we'll just decide we'll rely on here. So we'll get ourselves some labels. So we're gonna say IMU. Well, actually, we'll say I2C 0 SDA, which I might have just did that backwards. I did. Okay, so I2C 0 SDA, and then we're going to say I2C 0 SCL. The reason we're saying I2C 0 in here is the Pi Pico has two I2C controllers. And I2C being a multi-address, multi-device, multi-drop bus that's addressed, you can attach multiple devices onto an I2C bus. So we're just denoting here that we're using I2C controller 0. Just because if we do want to add other I2C devices somewhere down the line, we can decide which bus we want them on. And then at the very last bit, we're going to say IMU interrupt, which will be this. Perfect. And let's decide on our little thing here. We're going to use a footprint, and this is going to be a pin socket. This can be a socket. Pin socket, vertical. We want a 2.54 millimeter again. 2.54 millimeter vertical. We want the 8-pin socket, right? Pin socket, 2.54 vertical. Perfect. Oh, Jesus. Okay. KeyCAD crashed. It does that sometimes. Schematic. How much do we lose? Not much. All right. All right. So let's go back and fix that. 01 x 08 pin socket 1 by 08 P 2.54 vertical. There we go. Okay. Cool. Nice. So actually, I just want to see the 3D model of this. Just I'm curious. 3D model. Yeah, that's what it's supposed to look like. Okay. Cool. Now we have an MPU 6050. Now we need... What else do we need? We need to take a drink of fluids. Okay. Nice, so the next thing that we need to set up, now that we've got our MPU, we're going to add a servo connector, because we would like to have a servo that we can control with the Pi Pico to control the tilt on a camera, if we so desire, to be able to look around. I don't know if I necessarily want to set that up, but we'll add just so we don't have to pull the board out later. We'll add the symbol. So. We'll do 01 by 03. Generic, we'll call this the camera servo. Camera servo. Do a pretty standard servo connector, so that's going to be... this will be our servo control line. Get ourselves a label, servo in... And then the bottom one is ground. So 1, 2, 3, 4. Copy that. We're going to run the servo off the 5-volt rail just because of it's easier that way. We don't need to worry about providing a servo bus, or a servo power bus. We have one small servo, so we can get away with using the 5-volt out. And as long as we put the connector near the, I mean, maybe we put a capacitor on this or something. But generally no worries here. We'll just do that. Oh, no, just want to make some more space. Keep everything aligned. Yeah, I did a good job there. Okay, cool. Right, camera servo, and then the last two things that we need to do is set up the header for the LiDAR. And, all right, so, LiDAR. Okay, so the LiDAR needs two connectors. One is the data connector, which has the TTL serial input and outputs for the data connection to the LiDAR, and then there's the 2 pins for the motor control. So one is a 4-pin connector. And actually, before we get into there, we're going to define the footprint of this thing. This is a pin header, 1x03, P2.54 mil vertical. Okay. Save. Yes, and so now let's do our generic 0104 connector. This is our LiDAR data, our XV11 LiDAR data. And on here, looking at the pinout, we've got, again, kind of the standard layout that you'll bump into. I'll move this down a bit. We've got 5 volts on the 1, 2, 3, 4. On the top pin, we've got 5 volts. And then on the bottom one, we've got ground. And then in the middle, I believe we said that the orange was the data out, but let's look this up. XV11 LiDAR pinout. Oh wow, somebody got it connected to an EV3. That's amazing. That's cool. I like that. That's neat. All right, the cheap option, right? Okay. No, I just want the pins. You tell me what color things are. Okay. Yeah, here we go. So the. Oh, I wish this let me zoom in more. It looks like the transistor. Orange wire is the receive. Okay, cool. So on the LiDAR pin, the second pin is the brown one, which is the transmit, so you can send data to the LiDAR, but you only really need to do that if you're updating the firmware on the LiDAR, which I don't think there ever was a firmware update for these LiDARs, and if at any rate, we don't want to worry about that. So we're going to say no connect for pin 2, and then pin 3 is our data connection. So we're going to say, get us a little label here. This is going to be XV, this is going to be LiDAR TX. And then, all right, LiDAR data. And then now we need to do a tiny little drive circuit for, and actually, let me just, again, define the footprints. This is going to be pin socket 104 P2 millimeter vertical. Oh, and actually I did that wrong. JST EH. No, GST. It's PH is the 2 millimeter. PH 4 pin, right? Vertical. Connector JST. Yeah. Okay. Did the JST stuff here, right? Yeah, I did that correctly. Cool. All right, LiDAR data, and then now we need one final one, and this will be the LiDAR drive circuit. And that's probably the most complicated little bit that we have to put on here. But the LiDAR drive, we need to use a little transistor or something to handle the base, or to handle the current from the motor. Because as most of you probably know, can't connect brushed DC motors directly to microcontroller pins. The microcontroller pins can't source enough current, and also microcontroller pins that just cannot deal with the inductive load. And then when you stop the motor, that reverse current spike is just digital logic and motor coils connected just don't get along. So we need to do a little tiny low side drive for the LiDAR. So again, we're going to put hopefully our last connector here, O2. This will be the LiDAR motor, XV11 LiDAR motor. All right, so the way that we're going to do this is we're going to do what's called a low side drive. And that means we're going to put a transistor on the bottom. Basically, you're going to have the power in, you're going to have the motor, and then you're going to have the transistor that turns things on and off. The reason we do that is that I'll show you in a second when it makes a little more sense if we draw this out first. So see 1, 2, 3, 4. We're going to copy the 12 volt little thing again. All right, so low side drive. So we're going to, again, just because we're talking about things I can find on my shelf, for the most part, the only thing I actually bought for this project was the battery protectors, because I didn't have a good solution for that. But we're just looking for an NPN transistor. So again, you really do want to use a MOSFET for this in this day and age. There's no excuse to use to bipolar junction transistor, BJTs. Unless you have a specific reason for using them, you need you need a voltage to control the current. Or you need a current controlled device. Sorry, because the functional differences between transistors are or a gross oversimplification maybe, but a bipolar junction transistor, BJT, or what we would just call a transistor for the most part, they are what is called a current controlled device. The conduction of current through the transistor is directly proportional to the current flowing through the base of the transistor. They are a current controlled device. They have a factor that's called the gain, or typically the Q factor, or not the Q factor, HFE, which is the gain of the transistor. And so typically the current flowing from collector to emitter will be equal the current through the base times the gain. So again, the current from this C to E moving through the transistor will be equal to the current flowing from B to E times some gain factor defined by basically the transistor. And so we're going to be using some signal transistors, some high gain transistors that are they actually are literally from Radio Shack. They've been in my bin for a decade and a half. I don't know. They were called jelly bean components. They never break. I just have them. So a MOSFET, on the other hand, is a voltage controlled device. So the current, they're not called the same thing on the MOSFET. So for an N-channel MOSFET, which would be equivalent to functionally equivalent to complete different operating principles. But like circuit-wise, you could replace this BJT if you replaced it with a MOSFET, or an N-channel MOSFET would be equivalent to an NPN. Basically, NPN transistors turn on when there's a current. PNP transistors turn off when there's current. They're kind of reverse of each other. So, but anyway, N-channel MOSFET. The current so on an NPN transistor, this is called the collector, the base, and the emitter. On a MOSFET, this would be called the drain, the gate, and the source. And the reason source and drain look backwards, because people think, oh, well, this is the positive side, this is the negative side. Well, electrons actually flow from negative to positive. So if source being the bottom one, this is the electron source. And this is the electron drain. They're going out. So if you think there's positive and negative, the electrons are actually going from negative to positive. But anyway, for a MOSFET, it's a voltage-controlled device. So a voltage present on the gate of a MOSFET causes a current to flow. And so the idea is if you charge the gate, current will flow. And then once the gate's charged, the MOSFET the MOSFET stops consuming power. Or the gate stops. There's leakage current, so you can't quite say that. But for the most part, there's a the MOSFET stops consuming power. It only takes power to change state. It doesn't take power to continue to turn on. So anyway, but because I don't have any small N-channel MOSFETs available, we're going to be using just a little tiny BJT because I have some. I do have some power transistor MOSFETs, but yeah, those are way too big to use for this case. So we're going to be using just a simple NPN transistor. And so 2, 3, 4, and then we're going to connect that to the collector, and then this is finally going to go to ground. Oops. All right. And then there's this is a couple little final components that we need here. We need a resistor on the base, because remember I said it's a current-controlled device. So we need we'll use a 1K5 resistor, because again, it's something I have. So we'll do this. This is resistor 3. Okay. We need to put a resistor on the gate, because since it's constantly conducting current, we don't want to... or we just need to limit the amount of current flowing into the transistor. Because otherwise you can kind of think of this as... It'd be literally connecting like a... you can imagine the base to the emitter as a diode, right? It functions kind of like a diode. So it'd be like connecting your microcontroller pin through an LED directly to ground. It's bad. It sucks too. It just pulls too much current. So we're gonna say this is the LiDAR PWM, and we'll set that here and copy this. Move this over again to. All right, so 1, 2. Sorry. No. I don't remember how to shrink a wire. Anyway, so that's our LiDAR PWM. There's one last component that we need, because this is a motor after all. We need to do something with, this is a brushed motor after all. We need to do something with the flyback current from the motor. So we're just going to look for a standard jelly bean old diode, like a 1N, oh god, what is this little diode that I have over here? We have a, these are just like, these are again jelly bean diodes. These are 10O, 10O, I can't read. These are IN4001 diodes that I have. These are, again, probably a Radio Shack purchase, just simple signal diodes. So 4001 diode, classic diode. And so what we do here is we put the diode across 2, 3, 4. We put the diode backwards across the motor. Basically, this looks like it's basically opposite the direction of the standard current flow. So if you familiar with diodes, you can kind of imagine them as one-way wires, right? So what's going on here is let's fix this here. Sorry. Right. All right. So what you can imagine here is that if the diode is, you can imagine a diode as a one-way wire. The diode, the current flows from the top to the bottom. Or let me make sure I get this. I believe it flows from the anode to the cathode. Make sure I got that right. Anode, cathode, diode. Make sure I got the sides here before I exclaim. Yes, the anode is the positive side. The cathode is the negative side. Because okay, I got that right. Cool. So the current, or the electrons, will flow from the anode or from the cathode to the anode because the electrons go backwards. But in the circuit, you would think positive goes to the anode, goes to the cathode, goes to ground, and that'd be the way the current would flow. The apparent current would flow. Sorry. Positive. Yeah, I'm getting this backwards. So you would think positive anode, cathode, ground. If you put it backwards like this, well, current won't flow. But remember how I said that there's a flyback current? Any inductive load will have this, but a brushed motor is an inductive load, and therefore when you shut it off, inductors attempt to keep the current moving through them the same, right? So also the motor is still spinning, so there's a magnetic field induced. This is also called back EMF. But the motor, the moment you turn power off to the motor, it will start producing it'll produce a large current, a large spike in the reverse direction. So what this flyback diode does is, rather than shocking the power supply of the system with a basically almost, you can think of it as a battery plugged in backwards just for a brief second, or a brief tiny instant in time. What this current with this is called the flyback of the flywheel. I think it's typically called the flywheel diode. What this will do is it gives the current a place to go that is not the rest of your circuit. So when you this is a tiny motor, so we really don't have to worry about it that much. But like for the most, what this will let us do is when this motor shuts down, this dissipates whatever current spikes come out of the motor. And I think we typically call this the flywheel diode. Okay, so we have our little setup here. So we've got our LiDAR data, our LiDAR motor. We've got a servo. We've got our voltage regulator pins. We've got our these other connectors. All right, so let's decide where these are plugging into the Pico. So let me go grab the little board that we started building last time. And just backing up, So we've got. Let's back up. We've got. Let me turn my camera back on here. All right, so we got this board where if you remember, we soldered these little connectors for the Pico into it last time. I'll just unplug that from this bugger. So the Pico is gonna. Wow, I can see this, but you can't. The Pico's gonna go in like this, and then there's gonna be a terminal block over on the side, and we're gonna solder down our voltage. We're gonna solder in our voltage regulator like right here. So kind of look like it'll look like this for the most part. Be the arrangement. But let's decide. Based on where we want to put these connectors is going to determine where I actually which pins I connect the stuff to. So for the most part, oops, I would like to. I want to put the motor stuff down in the base. So what we'll do is we'll actually put the motor connectors under facing backwards so the motors can connect to them under the Pico. So we'll say that we're going to try to mostly use the top row up here, or what would be the basically any starting from here. So GPIO 28 backwards is going to be where we want to attach our motor stuff, but we'll leave the ADC inputs alone just because if we want to connect any analog stuff later. So let's look at the Pi Pico pinout to select which things we want to use anyway. So we shall. So on this side, okay. So if this is going to sit, we'll look at it on the bench in a minute. But if this is going to sit inside the robot, so this is actually going to be top up near the frame on this side. So the left-hand motor will be. Hold on. Sorry. So if I'm looking at this, if the robot's facing this way and this is sitting here, this will be the left-hand motor, right? Yeah, because the robot's facing me. The left and right of the robot, because it's facing me, the left and right are the same from my observation. So the left motor will be closer to the USB connector. So what we'll do, because it's close to the USB connector, we'll define, pin 1 of the motor is going to be, or how do I want to do this? Actually, we might just want to put the motor near the power inputs because of high current. So this is going to be on the input side of the voltage regulator. Actually, yeah, no, that's a good thought. Well, anyway, we can route the wires. We can route the wires however we want. But we'll just start assuming that we'll line things up, right? So if we do it that way, and we have our motor placed like this, the blue will be the higher pin. So the blue being our PWM, we're gonna do we're gonna start arranging this this way. So PWM direction tack. And then we'll do the right ones. That'll be the same problem, right? Right, tack, and then... Of course it didn't work the way I wanted it to, right? How would it work the way I wanted it to? There we go. Okay. Oh. I'm gonna put these here, and then the RX. Oh, jeez. All right. One nit. We need to put the tachometer one more up because we can see that the receive pin for the UART is on GPIO 17. So this actually needs to be our LiDAR, or this could be our LiDAR receive. And because there's nothing else going on over here, I think it probably just put the LiDAR input over there. So let's connect this up. All of our stuff. Okay, cool. Yeah, because otherwise it's a good site for the LiDAR. Okay. We're also going to just disable the analog inputs for now, just because we're not going to use them at the moment. Okay, so that goes there, and then we'll use. I'm just going to say we'll use GPIO 15 to drive the LiDAR PWM. If I rearrange this while I'm soldering things because it makes more sense, we'll do that. But so we'll do the LiDAR PWM there, and then we'll do the servo in over here, and then we'll do the servo. Should the LiDAR transmit servo in? Yeah, okay. Servo in. We'll do the PWM, the LiDAR. Actually, I think there might be Pi Pico PWM limitations. I'm trying to think, because 8 PWM, 2 slices each. Pin number ended to 1. Oh, okay. So basically, sorry. So the Pico only has so many PWM controllers internally, and some pins, I believe, are paired together. So if we... PWM slice is the number shifted to 1 and at output. Okay, so the frequency, we have to make sure we're on different slices. Okay, so we need to move this up 1. Just because GPIO, like 0 and 1 are on the same PWM slice. 2 and 3 are on the same slice. The slice has to have the same frequency. Which, because we need to alter the frequency to control servos, the servo's PWM frequency is going to be different than that of the motor. So or the LiDAR drive motor. So we have to make sure they're on separate slices. That's fine. We can deal with that. 13. Well, we don't want to. We don't. Actually, that's. So what we'll actually do is move this. Okay, so we're gonna do. What we actually need to do is move. Sorry, what I'm looking at here is we want to use I2C0 for the IMU. We could use it up here as well. Actually, it's fine. We're gonna say we won't use GPIO 14 and we won't use 12, and then we'll use pins 8 and 9, or GPIO 8 and 9 for our I2C. So that's I2C 0 SDA SCL. I'm going to be using UART 0 over here, so that's fine. So UART 1's the only thing we got left. Okay, it's available up there. So we'll make sure to use... Actually, realistically, I want to use 12 and 13, because that's one of the UART 0 sites, and because we're using it over here, it's fine. So actually, yeah, I'm going to rearrange this a little bit. So we'll put the LiDAR PWM and the LiDAR PWM, and we'll put the IMU's interrupt pin on this site here. And then we'll actually move the servo up to 1, 2, 1, 2. We'll move the servo up to pin 11, GPIO 11. So that'll be eating I2C1, but it frees up I2C0. And we still have an access to I2C1 further up, so that's fine. So we'll connect this, we'll connect this, we'll connect this. And then we'll use I2C SCL, SDA. I believe these are reversed. I mean, I think SDA is further up. So yeah, on pin 12, GPIO 12, SDA is the top. So yeah, we need to reverse these. All right. All right. So I think that represents all of the I2C0, the interrupt, the servo, the LiDAR PWM, all the motor control. Yeah, so that actually represents the entirety of the circuit for what we want to do now. So let's just go through here and briefly just tap out all of these unconnected ones. So if we, bring in our, so that everything's happy, all right. We're going to set this as, come in and do those footprints that we didn't do before. So this is going to be a 2-pin vertical connector. These resistors are going to be standard through-hole resistor THT. We're going to do our classic, quarter watt. I don't even know if the... Ooh, that's interesting. I don't know what size that's supposed to be by default, so we'll just leave that for now. Okay, perfect. So if we actually wanted to look at what this looks like on a PCB, we could say bring in the... We got a couple of things undefined, but we've got our layout things here. So we're not going to do that because we're not actually designing a PCB. We're just... what do you call it? We're just trying to do the schematic just so I can share with you what this schematic actually looks like. And so yeah, so this is what we got. This is good. This is what we're going to be building. And so now let me go. Now that my phone's finally charged, let me set my phone up on the mounting arm over there, and we're going to start soldering this together. And then. It'll probably take the next, hopefully I'll be able to finish this in an hour. But yeah, so let me turn off my webcam, leave the mic on just so I can moderate y'all while I'm doing this. Then we're gonna, I'll set that up. Okay, so let me take the case off my phone. Oops. And hopefully, I don't get everything inverted again this time, like I did. Or mirrored. Okay, so... All right, let me switch to the desk cam. Okay, let me try to make sure that this is all done correctly. For whatever freaking reason, this app refuses to have understand. Okay. Okay, so hopefully, let me come over here and check. Yes, I have the mirroring and everything set up this time. So Okay. Now, unfortunately, just so you can hear me, I need to use the phone's audio, which is really crusty compared to my desk mic. I really ought to get one of those lapel mics. Anyway, we're going to switch the audio source over to the bench. And maybe you can hear me from over here. Okay, just grabbing all of the stuff and moving over here. All right. Hopefully y'all can still hear me. Here's the LiDAR. Here's the other stuff. Okay, so the first thing that we're going to do is we're going to move the, well, just to give a visualization, the way that the terminal block here is mounting with the Pi Pico. So when I was saying that this is the, if the robot's sitting here, right, this is the left motor, right? So if this is sitting in here, the Pi Pico's USB is facing to the left, you know, so it would be, you know, on the left side of the motor, or the left side of the robot. So we're going to solder this, we're going to start working on soldering this voltage regulation module down, which should be Gucci. Okay, cool. Yeah, we move the robot on the floor over there. Hopefully the kittens are not disturbed at the moment. So we'll just take the LiDAR and let's grab the little connectors that we need. Oh, I hate this box. I hate these cheap component boxes because they never want to open. Then when they finally do snap, right, they fling everything everywhere, right? Okay, so we need one of these. We need 2 5-pins. Okay, fine. We need a 4-pin for the LiDAR. So this is for the LiDAR. I need a 5-pin, one 5-pin for the left motor, another 5-pin for the right motor. And we're going to, we have our MPU 6050. We're going to be a little fancy and use one of these low profile connectors to mount it. What else did I put in the schematic? We got the 5, we got the motor, the LiDAR, that. Okay, the terminal block. Okay, cool. So these are our little jelly bean, hold on. These are our little jelly bean transistors, right, from Radio Shack, literally Radio Shack. So we're gonna be, hopefully I can see through my torn packaging here. We can see that the typical, oh dear. The typical gain factor on any of these is 200. Well, I don't know about the 2N222, but it looks like because we tore it off, but all the other transistors have a gain of about 200. So that's fine. So, but we want the highest current, so we're going to take, I wonder what that used to say, but we're going to take the 2N4401 because that's the highest current transistor I have here. Realistically, the LiDAR motor, I believe on this, I think it only pulls about 75 milliamps in active while spinning, but the startup current can be 350 milliamps, and that would exceed the 3904's rating, which, I mean, for a brief instant, it's fine, but just to be certain. So we're going to look in here for a 4401. Here we go. 4401 transistor. I'm going to keep our pinout reference handy. I also have the diode that we'll be using, and that 1K5 resistor for the gate. I also need to find 200K resistors with pull downs. So let me go look at my ordered from an electronics supplier many years ago, a pile of resistors, right? So looking for the correct resistor value, right? So I couldn't even tell you what color 100K is, but I'll know it when I see it. There we go. There's one. Like, I don't even know how you. I mean, I don't know what that's called. Where I visually know what the colors will be. Like when I see one, I'll know it, but I couldn't tell you what they are. Um, I mean, before I see it, I couldn't tell you what they are. Now I can see that it's brown, black, gold, or brown, black, yellow is the actual color pattern for this. But I visually know what it is. And that might actually be, it's not gold. Yeah, brown, black, yellow. But again, I could not have told you what that was without looking it up. But visually, I'll know it when I see it, you know. Alrighty, goes away. Hopefully y'all can still hear. Okay, well, we got our two pull downs. We've got our gate current limit. Then we've got these, which are some value. I don't know what they are. Realistically, I got these so many years ago. I don't care for them. I think these are 4.7K oops, sorry. I think these are 4.7K resistors, but yeah, I just don't need them. And I got a whole freaking roll of them because everything I do these days is basically surface mount. But you know, I use them because I steal their legs when I'm doing prototyping. I just cut the legs off as scrap wires basically. Just kind of sounds kind of funny, but you know, here we go. Just steal some of those. We're gonna get our wire cutters, or actually, I mean, these are flush cutters, but you know, there's the wire cutters. I need to be kinder to my flush cutters. But all right, so I'm gonna power up the soldering iron and think about our layout here. So I was thinking, you know, because of this layout here. Oh, that's, what the hell happened to it? I don't even know. All right. I don't even know. Oh, jeez, that's gonna be fun. Now these are actually, you know, these are 2mm, and the more you stretch it out, you know, the less good it'll be. But you know, hey, whatever. Solder 2mm connectors to 5mm or to 2.54 mil. You know, the lining up doesn't work as well in the future, but hey, whatever. Will it fit? More or less. We'll make it work. Yeah, there we go. There we go. Evil, but why not? Put the line up. Okay, let me fix this. Hold on. No problem with holding this off camera, but anyway, okay. So, ow, fuck, that went under my fingernail. Okay, cool. So, I was thinking we could put these, I mean, what did we decide? We decided we'd start at not the analog, the digital one. So, 5, oh, I'm looking at the wrong side yet. GP A2, A1, A0, run. So yeah, GP22, right? We decided. Let me just zoom in this schematic for my sake so I can see it over my shoulder from. Okay, so yeah, GP22 is where we're going to start connecting the motor. So that's how far down? GP22 is, oh, it's right here. So yeah, I mean, heck, we'd start putting it right there. I mean, yeah, that actually would work out real nicely from a layout perspective, you know. So, oops. Oh well. Let's start. Okay, now that we've got everything up, let's start with putting in this terminal block, just because we know where we want this to go. We're gonna put it. Another design choice here is I'm trying to leave the upper two, or the two rows on each side free, just so if I want to, when I'm putting in the 3D printed bracket that's going to hold this together, I just want to give it space. So we're going to put this terminal block in and make sure I don't poke anything important with a soldering iron. Okay. That is one of the worst solder joints ever. Okay. It's because it didn't use any flux, that's why. There you go, let it flow. I'm gonna throw some flux on this guy here. That's fine. Okay, terminal block mounted. Hopefully we didn't melt anything too bad, you know? Okay. So now what we're gonna try to do is secure. Yeah, remember, easy way to tell on this one is the input. The input side, the higher voltage side, is got more. It has fewer has fewer energy storage capacitors, and so we're trying to basically place this down without shorting. I mean, I don't really care if we're shorting anything, but basically the the solder mask will save our butts anyway. So yeah, because these positive ones have less less coverage, right? I'm gonna in minus out minus. Yeah, but I'm gonna try to align the output side more closely with some of these pins, just to make sure there's less, you know, phantom conductor, you know, kind of pads under this whole thing here. Anyway, okay, well, here we go. Here goes nothing. I'm gonna try board-to-board soldering on a proto board. This is gonna be interesting. This is gonna be interesting. What we'll do is we'll add some solder here first, and we'll bring this over, and hope that it soldered it, sort of. It did. The corners tacked down a little bit. No. Try to move this over a little bit more. Yeah, there we go. All right, that worked. That worked. So now let's try to connect it on this side. Well, you can try to do something similar. There we go. We just gotta believe. Popped it again. Okay, that's funny. Cold solder joints are... Nobody likes cold solder joints for breakfast. Wow, it's all creating fun blobs of everything over here, right? Okay, it's probably really hot now. Okay, let's start connecting other stuff. Negative rails. Perfect. actually connected to anything down there, but one can hope, right? Okay, fine. Why is that still here? I gotta put that back in the thing. Interesting. Okay. Again, interesting. Where did this go? I just burnt the pad off on that. Oops. Okay. Well, anywho, I think it's connected via the bottom. Okay. I think it's definitely connected through via these some of these tubes or pads. Okay. Looks good. Okay, so that's good, that's good. We've got all of our little voltage regulator pads done, I think. Okay, nice. Let me just do some conductivity testing. Make sure we didn't short anything. Alright, so ground should be connected to ground, right? Yep, ground is ground, but... yeah, and that's basically not connected. It doesn't know what to do. And then these are not... I mean, it doesn't know. It's gonna charge the capacitors and freak the fuck out. Yep, not connected. I'm technically charging the capacitors in reverse. Alright. Yeah, it doesn't know what to do. The same thing on the bottom. I'll just make sure that these are actually connected. Ow, it's still hot. Yeah, so these are connected through. This is hard to... actually test this here. Yep, that's connected. That's not. Hold on, how about this one? Yes, that's connected. An easy way of figuring this out is testing whether these are connected. That one, oh. Yeah, those are very connected. Which is fine, because that's the ground side. We want that. And then that and this one. Oops. Ooh. And a good way of punching both of these simultaneously. Yes. All right. Our voltage regulator is connected up. Perfect. All right. So let me put this aside. Doke. And then now what we want to do is we're going to have to connect. We're going to have to bring the 5 volts up to the Pi Pico. But for now, what we're going to do is we're now going to connect the motor control stuff. Honestly, what I'm going to do is I'm actually going to plug the motor in just to make sure that all these pins kind of stay. Oops. See, exactly. We're going to make sure all the pins stay in where they're supposed to be. We're going to plug the motor in to this. Plug the motor into the housing. There we go. Cool. See? There we go. And all right. Use this just to figure out where we're connecting stuff. I'm trying to do GPIO 22, so here. How deep into the connector housing can one of these things slide? Oh, shit, I just broke the wires to the motor. Okay, well that sucks. Alright. Okay. Wow, good job, Nathan. I really sheared off the connectors to the motor. Okay, not my brightest moment. Not my brightest. Alright, precision tweezers. Alright, one down. Alright, plug that back in, push that back in. Alright. Okie doke. That was lame. Very lame. So now we strip the wire there. Strip wire here. Now you get to see how we actually put wires into these JST connectors, eh? Alright, we'll save that for a few minutes from now. Alright, so. How about we use, maybe that connector's kind of fudged up here. Here, we'll use this one. The only reason we're doing this is because since we're using a 2.4 mil, a standard 0.1 inch spaced proto board, we can't actually, you know, stick 2mm connectors in it. We're going to have a fun time here. And again, which freaking way did this go? Oh, is there a freaking ground right there? Okay. Okie doke. Alright, Alright, so we're just gonna wire it all up like that. I'll just float in here. The other one will go next to it eventually. Those are not exactly centered, but at the end of the day, does it really matter? I figured out. Alright. Oh, don't cool off soldering iron. Okay. Put up the iron. Probably gonna want to put some flux down on this. Flux pad. Alright. Let's try this. See what happens. Nice. 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 Alright, one left. One left. Okay. This one. There we go. Did it connect up? Yes, it did. It did indeed. Alright. Nice. So, that connected up all nicely. Perfect. I like that. Nice. It went well. See, we got our nice little soldered connectors there. We got our thing down here. And so, unlike last time where we sheared off the freaking everything, see if this, we're gonna bend the pins back out. Inside here. Should be doing that something a little stronger. Use these pliers. Oh, I bent it too far. Ugh. Oh well. If it's easier for you to see, it's harder for me to see. Sorry. Okay, I'm gonna try to use this. Okay, and not holding things by the wires this time. We're gonna do that. Seemingly, everything came back out correctly. Alright, good enough. I really think this one's broken. I mean, I think it looks like I melted it on a previous occasion, so we're gonna just get a different one. We'll use that one when there's a not definitely being used out of spec. When there's an in-spec project, not an out-of-spec project, right? Alright. We won't seal that up because we're going to need it. Okay, so here we go. Bend this to the side, bend this to the side. Again, only bending these things because we're trying to shove a 2 millimeter connector into a 2.5 0.54 4mm proto board. It's not the prettiest thing, but again, this is prototyping. There we go. There we go. I like it. Well, I really don't like how close to the voltage regulator module the other one was, so we'll just, and I don't like how close to the high rail this one is, so that's actually fine. It's to the side. That's fine, it's fine. Alright, what we're going to do is we're going to flood one pin, and then hopefully bend it out to the way that we need it to be. Okay. Flood one pin. That is flooded. We realign. Looks pretty good with this motor. And solder the rest of them. All right. Okay. All right. Well, let's see. Are those pins flooded? Yes, yes, indeed they are. All right. Perfect. We got our two rear connectors here that go to our motors. Will be perfect. All right. Now that we got those in, I like that. Now we're going to connect up our. It's going to be our ground from this, using this resistor Manhattan technique thing here. Okay, I need to just straighten this up. Perfect. Okay. Ugh. Okay. about that. Hold this up. The tweezers to do some alignment here. Right. Hopefully we can tack it down without too much fanfare. Alright. It's stuck. It's tacked. We'll put it on this side. Alrighty, cool. Got that tagged down. Good on that. Okay, so the whole idea was get a little bit secure on one side, get it very secure on the other side, and now we can go fix the not very secure side. Cool. There we go. So now we have our ground connector to our terminal block. And I would like to flood the rest of it, but I'm just a little afraid. I don't want to melt into the ground plane on this PCB, you know. I can't fill this one. I can fill that one though. Okay, cool. That one's not under the other PCB. Cool, I see. Good, good, good. Nice, nice, nice. Okay. I should also try to blob it over to this one, because this one's another actual. There we go. Cool. Yeah. Nice. Just try to link this one up here. I just there we go. Okay, okay, I like it. Perfect. Okay, let me check the comments, see if anybody posted anything. Oh, hi, how's it going? Alright. How's it going? Again, if anybody has any comments, questions, please ask. I'm trying to check the comments at least every once in a while. Okay, so, got our connector. Okay, we now solder the high voltage, the 12 volt side. It's not really high voltage per se, but you know, in this scenario, it's our high voltage side. All right, got it partially secured. Don't like how that was partially secured. I want it centered. We seek perfection. We accept good enough, but you know, if we're not striving for the best initially, we'll never get close. Okay. All right. I see you. There we go. Okay. Okay, perfect. We have got, sorry, we've got our ground, we got our high volt, we got our higher voltage. Okay. Uh-oh. Well, I hit, that's not necessarily good. Trying not to hit that. I accidentally hit the capacitors. We're gonna just do a good old loppy lop off of the extra solder there. That does not look good. Okay, that's a cold joint. Okay. That is a cold joint. Fix that. Okay, fixed it. Good. Okay, I fixed my mistakes there. Good, 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 good. Okay. I think. Maybe. Oh, an attempt was made. Okay. So. Alright, so now what we need to do is connect. We need to connect the higher voltage side of these motor inputs. And we need to connect those to the 12 volt rail of the battery. But how we'll do that is we can't. Again, the 12 volt rail's the far edge. So what we can do here is we could bring a wire up from here over to the input, but that does jeopardize my concept of. Actually, I'm thinking of mounting this in the front anyway, so we could probably route along the back up here anyway. I don't know I don't know how much I like getting, bringing 12 volts so close to an I/O pin on the Pico. I don't really like that. So what we could do instead is we could do the long route, and I mean. Good route on top. Thinking. Okay, what I think I'm gonna do is I'm gonna take a piece. Oh, I need a higher voltage wire. Well, I mean, higher voltage. Sorry, current capability. I mean, if I route a wire down here, I mean, that's not that bad, right? I mean, that's not under the voltage regulator, so I could do that and then Manhattan the freaking thing over. That's one pin off behind the LiDAR. Sorry, I'm thinking. I think I actually will take this approach. I'm gonna bring the 12 volts in this way, and then loop it around, bring it over to the 12 volt side of the voltage regulator. I think that's what I'm gonna do. And then for the then how are we going to connect up the grounds then? Those we can do on the, I mean, I don't necessarily do it on the back side. We can do them on the top side. Bring them over to the, at least bring it up this way. And the grounds are fine, but, okay, I mean, I could also use a positive. I could also use a shielded wire too. I could tap this here, bring this over, put it here, do one for each side. Bring across. You know what? That's what I'll do. I'm gonna, as far as exposed stuff goes, I'm only gonna do the grounds. So we're gonna bring the ground this way over, and then connect it up to the this, and then we're going to use direct connection to connect the 12 volt signals, just because it's more dangerous to have those floating around. All right, so that's what we're going to do. So let's start by putting the so we can bridge the data connections up here, then bring them down in. So yeah, we'll do it that way. Okay. We shall bring the ground. So we're gonna bring it up. And then we want to tag that, bring it down. Oops. Oh, dang it. Okay. Let's actually use the pliers. That'll be what it's supposed to look like. And then do that. Okay, so we'll do that. We shall then tap this to tag it down. Alrighty, perfect. Unfortunately, that means we just separated it up there. Perfect. Okay. We'll fix that now. I'm gonna have to burn myself. All right. Looks like we did. Well, we succeeded in not burning me. Of course I tore this off again. Okay. We need better. fix this again. Ever so getting closer to burning myself. Ow, fuck. Alright. Alright, so this time we're gonna solder it down here. Dang it. There we go. Something. There we go. That gives us up here. That did not work as I hoped. At all how I hoped. Not working at all. Okay, you know what? Fuck it. We're taking it out. Yeah, but because of the little twist I put on it, we can't get it out very well. Dang it. Okay, so let's try it that way. Let's see if we can induce better. Okay. I think we need to cool them back down too much. Okay. That'll work better. We'll just assume that'll work better. Okay, I'm going to cut this again here. And I was supposed to be regaling you with the wonderful sound of my voice, but I'm trying to figure out how to get this to go in there. Right. Apologies. Okay. There we go. Okay. Uh-oh. Dang it. Okay. Dang it. Okay. Oh, we're doing this. We're gonna tack it down. Tack it down. Perfect. We're gonna tack it down. All right. Okay. All right. Trying to see this here. Actually, we're gonna use the flush cutters. And oops. And then we're gonna use the soldering iron. Alright. Now we're gonna try to do the cross beam. Okay. Oh shoot, did you melt the connector? It's like melted the connector. Okay. Lovely. Okie doke. Now, melt the connector again. Yay, that's fine. So close. Hey, there we go. Looks pretty good. Still isn't just cold joint. Okay. Oh no, no. Alright, cool. There we go. Got it. Got it. Nice. Let's just. We're gonna have to leave that one in there for the moment, just because we're not gonna be able to remelt that later. Or if I cut that, when we remelt this side, we're gonna destroy the. This will fall out. So we're gonna leave that there just for the moment. And then we're gonna get another one of these. I'm gonna straighten this back out. It's one of those. In YouTube videos, typically when you're looking at soldering, they usually speed it up and do a voiceover because it's a very quiet thing. Typically. Screaming at burning myself here, you know. A little melty there. Ouch. There we go. That was a mistake. I have to be very careful about how much we allow to melt now, just because Hard to... Not gonna be able to re-secure things, right? Okay, there we go. So I'm gonna do that. Why is that not taking? I don't know. Okay, there we go. All right, now that that's there, now we can fix up this side. Okay. Actually, let me move that. I don't know why those are so melted. I burned the pad. Oh shoot! I burnt the pad on that one. Oh well. Oh well. Ow. Yeah, okay. Okay, cool. We've got the grounds connected on these motors. Perfect. Flow this just so we can. Careful, Nathan. Right. It could have also been a mistake. Okay. Okay, actually, yeah, let's make sure we don't actually cross the thing here. There we go. Okay. There we go. That's still bad. Oh, let's try this and see what happens. Let's try reflowing this now that we cut that off. It's probably going to go terribly wrong, but let's see.
Okay. It's pretty ugly, but if it works, it works. Just don't, this is not, let me put some flux on it. Miracle oxidation solver. Oh, perfect, yeah. Putting some flux on it and redoing that made it all nice and happy and shiny. Okay, should have done that before. Perfect, okay. So now we've got the, okay, now we actually have to connect that last little piece there, but once we do that, the grounds will be connected. Let's do that. Do that ground connection here. And then, all right, yep, ground's connected. Perfect, love it. Just try to fix this little fudge here. Oh well, that really doesn't matter. Okay, cool. Yeah, the ground's connected. Now it's time to do the positives. Oh, come on. No flex allowed. No. No shorts allowed. Alright, jeez. Okay. We're gonna put some solder on it first. There we go. Make sure to get some solder here. I can't have any crap happen to you if there we go. Okay. Gosh. Okay, we got that. Now, let's try to secure that. All right. Cool. some more. What is that's not secured. Okay, that looks more secure. There we go. Gotcha. Perfect. Got that. Okay. Ooh. 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 Okay. I'm gonna run that over to here. No longer than there anyway. Slack. Okay, so we'll leave that one. We'll do this one. Alright. Okay. Oops. Connect this one. Okay, there we go. Okay, let's make sure we've got some more solder. Make sure that. Oops. Okie doke. Looks good. Okay, sorry again. Trying to just figure this out. Okay, pull that over there. Now we can solder these up. Actually, before we do that, we want to do the logic connections between these. Otherwise, we're not going to be able to solder under these wires. So, okay. So what we're going to do is, oh, sorry, shaky phone. Any comments? What's your favorite solder flavor? Ooh, pure lead. Pure lead is my favorite solder flavor. Mm. Mm. Straight lead. Okay. Nobody wants to sit here and watch me solder, clearly. Okay. So let's get these data connections in real fast. straight up, just cross wire or direct wire. This might be a little more finicky. Alright, okay, cool. This is stupid. Alright, that's secured-ish. Alright. Alright, cool. I got the wire up on the back side. We can solder this up. Nice. Okay, so I believe that GPIO 26, where's my Pico? There it is. Yeah, GPIO 22. Oh, I fucking soldered it to the wrong one. Oh damn it! I soldered it to the run signal. Okay. Well then. That's a little annoying. So all of these are misaligned? Ah, well. Brilliant. Love it. Okay. Shit. Let me double check that. Hold on. Yeah. Goes in like this. Goes in like this. Bring it like that. It's connected to the run pin. Yeah, I connected it to the run pin. Why not? Brilliant. Brilliance. Utter brilliance. Okay. Gosh. Okay. Okay. I guess we're desoldering some things. Okay. Perfect. Perfection. Okay. So, odds are we're not going to be able to pull. It's only off by one, right? Run and then GP 22. Yeah. Okay. So we can try to. Now it's really working. Okay. Okay. See how well this comes out. I just want to use tweezers for that. Alright. Yeah. Just cut it off. Just cut it off. I'll do that. Still link it up, but we might just get away with pushing it over. We just might. Just might get away with this. Possibly not, but we can try. Interesting. Gosh darn it. Okay. Keep trying to save this. I don't know if it's worth saving. Okay, well, that's gonna be that one, and then then we gotta ground, and then we gotta jump over the far side here. Yeah, so we're just gonna, honestly, the best bet is just to try to solder on another wire here. Okay. And melting my connectors. can't tell if that's connected or not. It looks to be, but you never know. There we go. No! Soldered it to the run. Okay, hold on. There we go. There we go. We got it that time. Okay, cool. We did it. We did it, finally. Okay. Got the cross. Oh, my back. Oh, okay. Swear to God. All right. This is why designing PCBs is so much more fun. We can just have somebody else do this. Quick old melt on this. There we go. Perfect. Okay. Looks like we've got continuity on that. Okay. Ugh. I've done so much damage to this connector already. Okay. Wheel. Well, cool. Connector 1. Connector 1 done. No. 1 of 6. Hopefully the others will be a little easier, eh? Okay, so next we gotta do oh jeez. Okay. So we can either do, so we gotta take this next pin. This is gonna come 2 down because this is a ground. So do something like that. Oh jeez. This is gonna make it difficult. Difficult. So you know what we could do? We could root this under. We could root this under. Yeah, I like that idea. Okay. Just just be a terrible idea in 5 seconds. Alright. Alright. Before we get too far into that, we're gonna some solder. Tack it down. Undo the old bendy bendy. Bendy bendy. Close enough. Aye. Okay, cool. Got that tacked up. Okay. Nice. Alright. Nice. Very nice. Alright. Let's check the stuff. Oh, hi, baby. How's it going? Sorry, it's kitty cam time. Meow. Hi, baby. How you doing? You in there? Okay. Kitten cam time. Yeah. Pet the kitty. Gotta take the kitty break. Hi there, baby. Yeah. Yeah. It's okay, baby. It's booped in the face by the other one. Oh, yeah, you're okay there. It's okay. Yeah. Yeah, it's okay. You both purring? Yeah. Cutie. Isn't it a weird skill issue that you have to be exceedingly good at something to be able to correct mistakes? Yeah. Yeah, that always feels kind of funny. Yeah. Hey, baby. Yeah. How you doing? Meow. Yeah. You know, that kind of cry makes it sound like you need something. Meow. Are you okay? Are you okay? Okay. 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 Okay, baby. Okay. It's okay. Alright, so let's see. We're taking a break, holding the cat, you know? My baby. The kitten needs some snuggles. Hi, baby. Yeah?
Do you want down? Do you need down now? Is that what you want? Yeah? There you go. There you go. Alrighty. Kitten's given attention. Okay. Okay, finish the tea. Take a short break. Let me check the battery on the phone just to make sure we're not. Alright, let's check the battery on the phone. Just make sure we're not about to run out of overview. 53%. Alright, I need to get this done. I need to get this done. Okay. Well, thankfully, I think most of the crazy stuff's left over there. Ooh, boy. Kitten, don't be under the wheels. Okay. Alright, so we did that. We've got, okay, let's get the last of this. Just make sure that this is lined up the way we think it is now. We got GP22, ground, GP21. Okay. So what we're going to need to do is and Danish, I do recognize what your comment was. You actually have to be good at soldering in order to correct mistakes in your soldering. You know what I mean? Oops. Soldering iron went into cooldown mode. Aye. Working on it. Cool. There we go. Whoop. There we go. That's tacked. So I'll go. So this one's not. Oh, geez. Ow, ow, ow. Hey, kitten, please. There's really dangerous stuff up here. Hey, baby. Hey, baby. There's dangerous things. I don't need you up here. There are dangerous things. A little bit of sculpting here. A little bit of geometry sculpting. Ugh. Okay. This is where things get fun. Okay. I don't know if I'd call myself good at soldering. Definitely know what I'm supposed to be doing, but I still. This whole proto board thing is something I haven't done in a long time. I mean, I've done them somewhat recently, but like, in terms of regularly proto boarding all of my projects has been a long time since I've regularly done it.
connected. There we go. Cool. We've got all the little wires to one of the motors set up. And we've got our little 3D wiring thing there, and none of them appear to be shorted together. Which is good. We don't want them shorted together. Be not very cash money. Okay. So now we need to do the next block of stuff. And so we got GP22. Ground, GP21. Ground, GP22, ground, GP21, GP20. Got GP19. 1918, ground 1716. Okay. So I think we said what? 16 was the. 16 is the tachometer for the. So yeah, we need to bring this one diagonal. Yeah. Now, it's easier to narrate programming than it is to narrate soldering. It's kind of funny. Maybe it's because I'm more confident in my programming skills than I am in my soldering skills. Again, realistically, the way to do this these days is just to get custom PCBs done, but I do still have a love of soldering things together. It does feel nice. It's a little cathartic, you know, sometimes, other than the neck pain from looking down so long. But all right, did that. I'm gonna solder. Right, did that. Oh, wait, something's up. Oh no, that's fine, that's fine. That's fine. Kitchen alert, where are they? There's one in a box. There she was. Alright, and the LiDAR transmit is the next one. Oh, one that's just straight across, finally. No, it's not. It's not, because that's the ground. Okay. So we do a bendy bend again. Okay. Okay, we do that. Okay. Leave that the fuck alone. Oh no. Yeah. Okay. Time to clean up the tip a little bit here. There we go. Burn crap off of it. Here we go. Okay, not too much solder. Yep. All right. Okay. We got one more. And then, oh, right, we need to actually secure it. Okay. Okay, there we go. Cool. Secured. Oh, best solder joints. Be honest. Let's be honest, those don't look the best. Let's flux that up a little bit. Flux it up a little bit. I don't like the fact that that moved. The fact that that moved. That means it moved up here. It did. Oh dear. It means we need to. Okay. Did that. Okay, cool. Mostly fixed. Soldered up here. Getting dressed to pull down the frickin' overhead lamp. Can you not? Hey, Sequa. Come here, baby. Alright. Okay. Last data link here. Alright. Last data wire. Okay. Alright, I got that. Lift up. Eat. No, don't eat that. Sorry, they are eating the robot chassis. Or they're trying to play with it, not eat it, but They killed my freaking Bluetooth cable earlier, presumably last night. But I don't need to repeat that. Secure that. Alrighty. I got that. Sweet. I got that 1, 2, 3, 4 ground. Okay. Well, I think that is it for the links for the motor data cables. Perfect. Okay. Now we can tie the power lines on. Maybe. I think I need to strip off a little more insulation on this one. I actually just want to twist these together too. Oh, that didn't exactly work. Okay. Ow. Ow. Whew. Okay, that worked. Somehow. Okay. Got it. The two wires hooked up. Okay. They're hooked up. Okay. Let's try to cut some of this excess off here. Okay. Nice. I like it. It's a good joint. Reasonably okay joint. Okay. So I didn't just damage that wire. Come off it. Okay. Checking the quality. Okay, well. Okay, well, time for some validation here. Okay, here we go. Oh no, don't do that again, Nathan. All right. Right. So we're gonna check polarity and continuity, stuff like that. Okay. So Okay, my back. Alright. Okie dokie. We've got the ground. You can see that the ground is available on the second pin. Available on not the first pin. These are grounded. That's ground, and then this is nothing. Alright, cool. Oh, we didn't put in the freaking resistors. Okay, we'll have to do that. Which one's the PWM again? PWM is the blue one, right? No. PWM is the... Yeah, PWM is the blue one. Alright, the outer one. We'll just do those up top, I guess. I'll just gonna fucking pull this through the center here. I'm we don't even do the leads here. Just do that. I just think of a good place to stick it. Hold on. Okay. Yeah, we're just... Okay. Dangerous move, but... I didn't burn myself, but I didn't succeed much either. There we go. Okay. the resistors here to pull the PWM line down. Okay, cool. Cool. Let me just fix this one. There we go. All right, cool. Let's do the other one. So these are the pull-down resistors for the to make sure that we have that is a diagonal of 3. One, two, 1, 2, 3. 1, 2. Almost there. Almost there on the motors anyway. All right. Okay, cool. We're good. We're good. Okay. So now I think before we can, the last thing we even have to do before testing here is bring up a 5-volt lug on the Pi Pico. I think it's the only thing we have left to, major thing we have left to do before we can test something anyway. Okay, let me double check the resistance is here. If we go to, I mean, it's kind of everything realistically, ideally. So we go to ground, check the pin. 100 K ohms. 100 K ohms. Nice. We shove it in there. I should be able to 100 K ohm. 100 K ohm. Perfect. Okay, I got that. Okay, yeah, so let's take a 5-volt tap from here around to the other side. Yeah. Okay. And that should give a. Then we'll pull the power switch out of the robot and hook that up to a battery protector and grab a lipo and hopefully test the motors anyway. That'd be really nice. It's starting to get late anyway. Yeah. Oh, breaking my rule. Hold on. We're keeping out of the keep out zone. Alright, hold up. This is how we're gonna do this. I hate this. Okay. But that's fine. I can hate this so the rest of you can enjoy. Ow. Okay. Root this here. Okay, we do this. All right. It's not working. Oh, yeah, it's the multimeter being like, yo, you haven't touched me. You haven't done anything. You haven't multimetered in a bit. All right, do this. Okay. We did the world's worst solder junction there, but there we go. That's better. On the hot iron. Alright. I have to hook up from the voltage regulator. Nice. Okay. Okay. All right. So that should yield. Oh, you know what? We didn't attach any of the Raspberry Pi grounds or the Pico grounds to actual ground. Okay, let's do that real quick. Sorry, we need to connect at least some of the grounds on the Pi Pico to the actual board ground, so we can actually get some connection. Oh, Nathan, put any solder on there. And you expect a connection to be made. Ow. I deserved that. Okay, so just to verify that that worked, let's plug the Pico in, and we're gonna do a continuity check. Make sure that the 5 volt goes to the 5 volt. The 5 volt out. This is the 5 volt in. Oops. 5 volt out. 5 volt in. Perfect. If we flip these around, we should be able to measure the diode drop to V6. That's funny. I think that's ground, right? V bus V6 ground. Yeah. That's not the one we connected, so we should be able to see a low resistance connection between this ground and our battery ground, which we do. Perfect. So we've got grounding there. We've got connection here. Perfect. Okay. So we got our 5 volts coming into the Pico. We've got our, and it's not the, they're not together or anything. Nope. So, yep, and the resistance goes up as the capacitors charge from the multimeter probe voltage. There's no short between there's no short between the 12 volt rail and 5-volt rail. So yeah, I think we can actually do some motor testing. Since it's taken me so much longer to put this together than I would have otherwise hoped. Let me check the comments. Where is the ground? Like, oh me, look, it's down on the floor. Yeah, basically. Okay. So kind of get an idea of where this is going in the robot, just again, so we can visualize this, right? This goes in here. Actually, let's all of these to the side, right? This is gonna go in here. And, you know, it's cut to fit, you know, with flush pretty much. Yeah, so that'll go there. We're gonna build a cross beam kind of thing that'll screw into some of the connectors up here to hold the thing in place. Yeah. So that'll ought to be good. So yeah, let's actually take this switch out and solder it up to the battery protector so that we can actually test with a real LiPo. So yeah, I think, how do I get this stupid thing off? Yeah, let's power the soldering iron for now. Put that to the side. Sort of, kind of, barely clean up my work environment here. Such a mess. Okay, so a mess. Sorry about the mess. I always tell you, keep a clean work environment, otherwise you're going to hurt yourself, and I definitely agree with that, but in this case, just, okay, motor, this stuff, right, and so we're going to pull the bolt here. I've done this in forever. Okay, switch comes out. Perfect. All right, so let's take the insulation off here. These wires have gotten really short over the years. Cutting at them and cutting at them and cutting at them. Okay, well, this should be shorter. Okay, hair shorter. Yeah. I'm gonna cut that one a little too short. Oh well, it's fine. It's fine. Turning the iron back on. Hey, baby. Probably close to another kitten break here. Kittens are getting a little beat. They're like, why aren't you paying attention to us? We're Ow! You. Grab you. Yeah, look at this. Look at this cat. Standard Mark I cat. Hey, baby. Hey, baby. I know you're cute and you want to explore the desk, but it's dangerous up here. There's hot things. Huh? There's hot things. I don't want you to get burned. whoa, careful, cat. No. Alright. No, no. You go down there. Alright. Alright. Use this. Mount the okay, got that one. Okay. We've got, we didn't wire it backwards, right? It's correct, right? We got red to plus, black to minus. Kittens. Okay. I think we don't need the soldering iron anymore. Just make sure I cleaned this up. Yeah, let me just put some fresh solder. And then we'll okay. Turn off the iron. That over there. Okay. That's probably fine. Black to negative. Okay, let's. Okay. Okay. Cool. Now we've got the whole thing covered. And alright, so we've got a protected battery, presumably. And so now we're going to get the screwdriver. Black is the low one, red is the high one. Built this. All right, I got that. Okay. Perfect. So, in theory, we should get, if we go grab a lipo, go grab a lipo. Okie doke. Lipo. Okie dokie. See what happens. The motor should not turn on. Uh-oh. Uh-oh. A couple of pens a little bit. It's fine. That's interesting. Okay. Oop. Huh. Uh-oh. Did I hurt this one too? Watch me have hurt this one too. Yeah, watch me have hurt this one too. I love it. Okay. Fuck. How do I keep doing this tonight? Okay. We crushed the pin, the fucking pin housing. What the? How did this happen? Okay, fine. We gotta rewire this one too. All right. Okay, they're all broken. Okay, brilliant. All right. Okay. Well, you guys get to see how we wire up these JST connectors. Cause they're all fucked. Okay. Little. Okay, that goes there. So what we want to do is get this on this piece up. And we'll take this, pinch it a little bit just to help. Okay. Only reason I'm doing that is obviously we want to crimp it, but it makes life a million times easier if we just, you know, in order to. Come on, get in there, you little. All right. Sometimes it's hard to get it in. It's hard to keep it vertical in the crimp tool. I hate this sometimes. Okay. ever so slightly trying to guide this into the crimp tool. It's just, we need, don't want this to rotate. I need it to, there we go, more or less. More or less that's how it works. But, there we go. Okay. I might have done it right. I might have done it wrong. We'll see. See how well this is crimped. Oh well. It's not a current carrying anyway. It's not a high current wire. Okay. Oh, it's back in there. So let's figure out what happened with this connector. I did literally break my connector to try to put this in here. There we go. There we go. That didn't break. Okay, cool. So wired that up. Wired this up. I know we double checked it a million times, so we're gonna power this up. Oh, hopefully it doesn't explode. Why is this still turning? Okay. Okie doke. Well, we're gonna have some fun with these motors, I guess. Might have had a PWM signal on that, I'm not sure. I have no idea. If it defaulted to pull-ups or it's an output of some kind, we just don't know what'll happen. Oh, I'll tell you. The pin we connected this motor to for the PWM is the same. No, wait. Might be the same we used for the LiDAR. I don't remember. Let's try that one. I gotta make sure that we got these pins unbent. Otherwise we're gonna destroy the freaking connector again. Let's not destroy my tweezers either. Might be too late on the tweezers. That one's also slowly spinning. Well, slowly spinning is better than quickly spinning, I guess. I don't know what's going on. Well, we didn't blow anything up. Well, that's good. So let's fix the motor wire for the other one. Or let's fix the cable for the other, and then we'll tweak our Picobot thing again to correspond to this new schematic here. And yeah, let's take this. Let's take, yeah. We are almost there, people. We're almost there, chat. Well, actually, we're not almost there. We still don't have the LiDAR or any of that hooked up, but at least we're almost to testing anyway. Or testing of something. That's gonna be one of those interesting in hindsight, but it's not the most. If anybody has any ideas on how to make this soldering process more interesting to watch, You know, like, Nathan, don't pull the thing out of view when you're trying to fix the wires. This is going to be causing me problems again. Oh, I crushed it too much. Okay, brilliant. Oh, Jesus, why is it so soft? Try to use, you have to use the right crimp setting, otherwise it'll slice the freaking wire in half. Come off it, I don't want to waste these. There we go. Okay. What? Okay, pull it off again. Okay. Oh, wow. You know, now we're entering the part that's going to take the longest. Yeah, it slips off easy, but it doesn't go back on easy. Fun. Fun. Nope, it's all over again. I really, really hate crimping these tiny ones. It's just the freaking worst. Okay. I'll be a little cheeky here, and we're going to try to use the pliers to hold the thing in shape. There we go. Oh. There we go. Oh, and it didn't even crimp correctly. Wow, look at that. Didn't even crimp. Didn't even crimp right. I'm over a lot right now. It's getting late, that's why. But, try again. Okay. I'm striking out on this tonight. Okay. Okay. There we go. Finally, we got one, I think. Yeah, looks like it. Perfect. Okay. I got one, chat. No, we got... The necessary part of this, you know, whole electronics thing, designing bit is necessary. The soldering, it's just always takes me a tad longer than I anticipate, you know. Alright. Looks like that's good too. Perfect. Okay. Okay, there we go. Alright. Put that in there. That's backwards. Okay. Okay, I got that one, and then this one. Alright, perfect. Little short on some of them because of this debacle, but oh well. And now we're gonna plug this one into the other. Alright, why is this freaking out? Don't freak out. Nope, I'm feeling that stupid thing where it feels like it's gonna crush the connector again. Okay. Tolerances are not great. Ugh. There we go. Perfect. All right, cool. We've got our motorized contraption here. I'll bring it over to the desk. Stream pirated Family Guy with Russian subtitles. Yeah, pretty much, right? Aye. So, let me grab the phone. Alright, we're gonna grab the phone. Ooh. Rarely do I feel it this one. Okay. Dude. And we're gonna switch. There we go. Just trying to change all the audio. There we go. Just trying to change all the audio sources back correctly, you know. Ooh, 11%. Took 90% of my battery to stream that video. Okay. Start that back up. All right. Perfect. Whew. Okay. Oh. Based on this schematic that we have doodled, we're going to come back to the... Oh, actually, we're going to come back to what we built, or the code that we wrote earlier, or last stream. And let's plug in the data that we now have for... because we've changed a couple of things if I recall. So if we go to this motors header, what did I remove here? Oh, the whole left encoder, right encoder. Right, okay. So the LiDAR PWM is now GPIO 15. And the
the tachometer, or so we got motor left. We've got 22 on the PWM. 21 on the direction. We got 20 on the tachometer. And then for the right motor, we've got 19. The direction is 18. And then 16 for the encoder. And then in here, if we come back down, GPIO set function. Actually, we don't want pin 16. We want 17 because it's the transmitter, but we don't want 16 here. All right, so if we this hopefully compiles, right? We'll pair my DualShock, which might work. It might not work, considering my cats ate my my Bluetooth antennas. So, oh right, I turned Bluetooth off because it was broken. So we'll turn that on. See if it actually. See if there's just barely enough antenna. Okay, that's funny. All right. It's not great, not terrible. Alright. It wasn't enough to stream audio, but it might be enough to stream this. Oh, and I forgot the battery. Okay. There we go. What time is it now? 10:28. We've been at this for 4 hours. Okay, so we'll plug the debugger in here. So debug, there we go. Plug the debugger into the debugger. And then put the battery, plug the battery in. And then we're gonna unplug the phone. We're going to plug the debugger in. And we're going to turn the battery on. And then we're going to flash the code. And if we get lucky, maybe it'll still connect to Wi-Fi from last time. Well, the motor stopped rotating, and that's a good sign. So if we source, that's the wrong freaking project. All right, so if we source virtualenv, and then we do Python, Python tools balancer control. Maybe we will be able to... Oh! Nope. Why is it not? Entering remote control mode. Why is it not moving? Why does it not move? Well, there... For all I know, there's not enough... No, I mean, nope. There's... Motors aren't moving, but... The controller theoretically is connected, and the motors aren't spinning anymore. So, oh, they're spinnable. That's interesting. Did I set these motor things wrong? PWM 22, direction 21, coder 20. Okay, well, 1918. Well, it is entirely possible that I am... Sorry, where am I trying to go with this? It's entirely possible that I've wired up the motors wrong. I don't think I did. But possible. It's also possible that this just isn't actually running because of the... But no, I mean, I can control the mouse. Oh, connection refused. Oh, well, that'll do it. Oh, maybe I control C. Maybe that was... Who knows? Who knows? Okay, let's undo what I was doing before. Main thread. Let's put a breakpoint here. And then unfucculate this other thing I was trying to write. And then we'll compile. And then we'll flash. All right, terminal will be closed. And then maybe we do that. It's still not running. Oh, I mean, who knows? Actually, yeah. Okay, what are we doing here? We ought to run the debugger. That's what we ought to do. We put a breakpoint. We recompiled. Pico debug. Racing chunk. So it's running, presumably. Terminal. Part of me hopes this doesn't work. It'll be easier to deal with. Yeah, there we go. It's not hitting the breakpoint. Oh, there it goes. And Y, X. Oh, hey, they're running. What? Oh. I hate when things work when you debug, but then they don't work when you're not debugging. Like, what even? Clearly, I wired them up right because they're spinning. Yeah, that's a good thing, right? So we'll... Right, what am I doing? Right, Pico, we'll just flash the project. And they turn off, which is good. Right, okay. Async lag from when you hit the breakpoint. It's possible, but I mean, I think this happened to me the last time too. It's also possible I just hadn't waited long enough. Alright, so let's 5, 10, 9, 8, 7, 6, 5. Oh, and the controller disconnected because I lost the Bluetooth connection. Because, again, no Bluetooth antennas. Wow, it's not... I'm blaming the controller, honestly. Or my lack of Bluetooth antennas is what I'm blaming. Because, I mean, heck, see, the driver's not... Oh, it's the controller's very laggy. So... let's see. Is it able to service not known? Sock adder. Oh yeah, everything's having fun times. Aimer service not known. Oh, is this not connecting to the Wi-Fi? Who knows? Who knows? Yeah. Flash project. And we're going to say ping picobot.local. Pico Pibot, yeah. Pico Pibot not known. Here. Oh, hey, baby. You know, another. The Kimpton is wants attention. Hi, Kimpton. Kimpty. Yeah, see, name or service not known. Yeah, it's possible that it's just not connecting to the Wi-Fi. So let's Oh, nope. Get down, Kimty. Nope. Ah! All right. No. What IP address has Pico PiBot supposed to be assigned anyway? 22. No, 1 here. What address should it have been assigned? It should have been assigned Pico PiBot is 233. Ping 10.00233. Oh, it's down. It's not up. Of course. Of course. What if we power cycle? The Pico. Maybe it'll come back up. Also, I really want to get... There we go. Alright. Pico PiBot, maybe. Yeah, there we go. Alright, cool. So it's definitely up. And now we do the controller thing. Oh, now they're working. Okay. Oh yeah, definitely lag on the controller end. It doesn't. It's registering like every fourth input. Here, let me bring up Droid Cam again. Yeah. So as we can, now it's Jesus. When I don't want you to remember things. And do. Okay, is that correct? Yes. So, forward, backward. We can control the motors. And they dance around. So, there we go. We've got controllable motors over Wi-Fi. On a Pi Pico 2W, on a DualShock that's trying to connect to my computer without Bluetooth antennas, and on our little custom PCB that we've been building with our custom board, our regulator, our wiring here, our battery protector module, our switch. So yeah, there we go. That's a good test, at least for right now. So let me get back off my phone here. Desktop. Okay. We are coming up on... We are past the 4-hour mark. Okay. Or are we? Yes, we just passed the 4-hour mark. Okay. So, that's still on. Turn that off. There we go. So let's... What are we going to do right now? Since my phone's dead, for now. What we could do is... Let me take a kitty break. What we could also do is start modeling the... I mean, it depends on how late we want to stay up here. I want to stay up here. Another thing we could do is start modeling the holding brackets for holding this thing into the robot. And let's see... yeah, so what are we doing? What am I doing? Yeah, sorry. So, let's see. What to do now? Yeah, so maybe the brackets, maybe the Also, a question: do you want me to? Do any of you want me to finish the soldering off camera, like between now and the next stream? Because we do still have the LiDAR driver and the IMU to do, but part of me really just wants to do everything on stream. But clearly, clearly, based on what I'm looking at right now, nobody really cares to watch me soldering. So let's see. Well, anyway, let me grab the robot chassis and let's start taking some measurements on designing the holding brackets for this thing. We'll fire up FreeCAD, spend the next 30 minutes doing one of the brackets. Maybe I can get the thing on the printer tonight. Let's find out. I'm gonna turn off the camera again for just a second, grab parts, grab my calipers, and we'll start doing some FreeCADing. All right. Grab the robot. Well, actually, I'm talking in the reverse order. Yep. Calipers. Robot. Okay, I got the stuff. I got the good. I got the meat. Meat. Move trash out of the way, and we. Okay. Battery over there. Disconnect the controller. Bring up FreeCAD. Okay, and we're going to do a new project, and we're going to call this project. No, you put this in modeling. You're going to put this. We're going to call this Pico PiBot dot FreeCAD. Do a part. I'm going to rename this part to be lower bracket. We're going to do a body. Rename this to lower bracket body. We're going to start with a sketch. But first we need to know what we're doing. So the idea here is this is going to be the bracket that... Oh, wow. Let me disconnect the motors here just so I can finagle this thing around. Okay. Unplug the debugger. Okay. So, given robot, and let's hide all of the wires. Oh, we got the curious kitty, Kimty. Right. So, given. I'm about to get my leg flensed. And then... Alright, so... If you can see on my camera that the fact that we want to hold the board in here, we're going to start working on the bracket that mounts to these little lower tabs and then holds some of the mounting points on this, the two screw holes on this PCB. So we're gonna start with that. All right. So, and then the idea is we're gonna mount it to all the way across on these tabs, and ow, kitty, that hurts. She is very cute. She's so look at this cute little gremlin. She's so adorable. They're so very curious. I just wish they wouldn't eat my Bluetooth wires, It's the only wire, well, that and one random jumper wire. Basically, they figured out how to get up onto my desk last night, and I'm not quite sure how. Heck, I've been pushing my office chair over to the corner so that they don't, You know what? You probably are actually okay to be on my desk right now. This isn't the soldering iron, and I think I got most of the tiny wires out of view for you. Well, actually, the motors are right there, so that's not true. But the hope is that if I let them up into certain places, they'll be like, there's nothing interesting, and then they won't try to go back. And then maybe if they don't step on my keyboard either, But, anywho, let's start with a XY plane here. Oh, there, she's batting at the motors. No, don't do that, kitty, please. Please be good. I mean, you are good, but you just don't understand. You don't understand why you can't eat the wires. Stop eating my wires. Come on. If you just sit there and look cute, you can stay on the desk. I mean, heck, you can even walk around. You just can't nibble on the stop. You just can't nibble on the wires. It's okay. I still love you. It's okay. It's okay. I just... You know, hey, I know. You know, I'm going to put you down now. I'm going to put you on the floor. There you go. Immediately turns around and runs back up my leg. But yes, so we're gonna. Yeah, so what we're going to do, we're going to make a little bracket. It's going to about bolt to all of these little tabs, and then the PCB will sit wherever it's supposed to sit. And we just got to make sure that we know the dimensions of this. And so the idea is that the little mounting piece, I'll probably make it as thick as these channels are deep. Or, well, basically the distance from the end to the middle of the channel I'll mirror to the other side. Anywho, let's start taking some measurements on that. So, we'll zero that. The outer is... Oops. The outer is... hard to measure because the tires are getting in the way. Is exactly 100 millimeters. It's almost like somebody designed this whole thing in metric. Interesting. 100 millimeters. Exactly. Wow. Alright. So 100 millimeters end to end. And then on the inside, it's 87.5. So it means basically, so the hole for a M3 bolt will be, what is it? It'll be 2.8, or it's supposed to be 3 millimeters, but the drill size is typically 3.2. So we'll do the spacing at, say, 88 for the insides of the drills. And then actually, we have another reference point here. 94 millimeters. So if we space the drills, no, because that'll put them there. So if we do, basically, if we put the drill spacing at 90 millimeters, I think, or what do we say, 87.5, and then we're going to add the, basically 87, or we'll say 88, and then plus 3.2, so that'd be 91.2 on the drill spacing. So we'll do a centered rectangle, and we're going to put 2 drills. These are going to be equal. Well, actually, the drills are 3.2, but we got to do we're putting in threaded inserts, right? So we got to do these will be 5 mil We'll do an equals constraint, but there's the jumper. I was wondering where they ran off with it too, but we're good. There it is. Do an equals constraint. We're going to set this to a 5mm hole, just because of that's what it needs to be to, or that's what it needs to be to stick a threaded insert for a 5mm or for a M3 threaded insert. And then we'll just make the whole thing 100mm wide. So we'll do 100mm. And the spacing on these, or actually, I mean, we made spacing on these is going to be distance. It's going, we said it's 88 plus 3.2. .88 plus 3.2mm. Okay, and then what we will do is we'll do 1, 2, 3. Oh, I missed that. 1, 2, 3. And we'll do a symmetric. So they'll be equally spaced. And then we need to do a depth. And that probably is just easiest to do. Quick measurement here. 4 point is going to be 9mm, because it's 4.5 from the middle of the slot to back. So yeah, so that'll be our mounting jig there, and then we're going to do a quick pad. Oh, did I get that wrong? Oh dear. It's more like 4.75, so that's gonna be 9.5 actually. Okay. So do that. We're gonna pad this out to basically small it can be. How big are these holes? These are, ooh, these are, these are M2.5 drills. So that means that I need to do I do not have much margin on this. Interesting. Yeah, I really don't have much margin on this. I've got, that'd be one layer line. That's awful. Well, I guess we can see. Again, we've got I kind of wonder, do I have any, I think I have M2.5 bolts. I just don't know if they're, how flush they'll sit. Let me grab those real quick. Let me turn on my webcam here. All right, M2.5 bolt. That's M2. Not that. Okay, found them. We've got, see how flush these things will sit. Basically, we're wondering whether I can use bolts instead of using threaded inserts, just because I don't have much. I don't know if I have enough margin to fit the threaded inserts width in this channel. So we're gonna say, let's grab one of these bolts. I should say screws. It's a bolt. I'm intended to be used with a nut. It's a bolt. No, it's not snacks. It might just be the same issue as the threaded insert. Actually, it's fine. They'll sit flush if I rotate the nut to the right spot. Okay, we'll actually design it around doing that. We'll assume it's a 2.8 millimeter drill for an M2.5 bolt. We'll just call it an even 3 millimeter just to be certain. But yeah, so we've got only about 2.25 millimeter. Why didn't it just be 2.2? We got 2.2 millimeters between the hole and the edge. Or actually, sorry, between the center of the drill and the edge. So if we put a 3.2 mil drill, we're gonna have less than a millimeter of wall. I mean, that's fine. This isn't really taking up too much a load. But the 9 mil depth might be a problem. Let me check how long of an M2.5 bolt I have on hand. Again, I'm going to turn off the webcam. Turn off the webcam. How long of an M2.5 bolt do I have? Oh, I've got some long ones. Okay. Okay, we're good. We're good. I've got some long ones. Okay. So, perfect. I've got some long ones. So, we're going to pad this to vertically. We're going to pad it to. And we really only need 5 millimeters, right? Well, if it's 2.25. Well, if it's 2.25, you know. 2.5 maybe? Yeah, it's 2.25, so it's 4.5. So yeah, we'll pad out to 4.5. And well, actually, 5. We need to pad to 5 because that's how long the threaded insert is that we're going to need for the other bit. Okay. Right. So, close the sketch, which we did. We're going to pad that to 5 for the depth on the threaded inserts here. And then we're going to need to plunk holes through this. So we're going to look at the front. Do another sketch here. I'll put 2 here. We're going to call this constrained symmetric. Oh, did I make those about the yeah, I made those about the origin on accident. Okay. Doop. The line. Sorry, it's constrained symmetric about the line. There we are. And then we want to do GX, bring that in, and then, well, we don't actually have to do that. We only have to do this distance, which is 2.25. And these are going to be equal. And this is going to be a 2.8 mil drill. And then we just need to define a distance from center, or a distance that they are apart from each other. And that's going to be, let's measure this. Oh, let me take this bolt out. Take this bolt out. Okay. So we got on one dimension, so on the outer part is like 87.7, and then the inner is 82 point, or it's like 82.5. And maybe it was only supposed to be 85.5, 87.5. Yeah, 87.5 and 82.5. So if we bring up Python and we do 87.5, 82.5, we want the midpoint between those. So that's just 87.5 plus 82.5 divided by 2. 85, I should have knew that. Okay, so if I dial 85 in on my set of calipers, hold those there, those, yeah, 85 millimeters, perfect. 85 millimeters. All right, and that's going to interfere with the threaded insert, because of course it is. That's lovely. How about we change how we're going to do these threaded inserts, and we give them a bit more spacing. We do 94. We're going to use the outer part of the tab here. So yeah, what if we're going to do a pocket of all the way the hell through? So we'll just say 10. Yeah, but we've cut into the threaded inserts. So we're going to go into our sketch. We're going to define this as 94 between the drills. Clear 94. I make this like 102, 104. Okay, close. And now we're not cutting through the threaded inserts as much. I wonder what the wall is though. Like, if we do that, we look at the distance, does that make any sense? No. Okay, well, we'll be able to look at it in the slicer. So we'll just print out this simple piece for now. This will give us the ability to tweak, or we'll easily tweak the slider. This will get us off the ground in terms of mounting something. Bed. Yeah, it's 11 in it. I'll export. Save that, bring up our bamboo slicer. And then we're going to do modeling, STL, Pico PiBot, yes. Yeah, that stinger adapter plate thing. Motor adapter, yeah. Sorry, STL, Pico Pico Pi bot over bracket. Yup. I'm going to do that. And then, because of the tolerances, we're actually going to turn this vertically. It just makes it easier to... that face. Yeah. It makes it a little easier. Sorry, what am I trying to say, right? The smaller holes don't print quite as accurately vertically, so there's tolerance with the threaded inserts. I don't really care so much about if the holes are perfect or not, because we're melting them in there. But because these are supposed to be like bolts stick through this, we kind of want these to be strong. So we'll slice it this way, and we're going to print it with blue PLA, which just make sure it's, yeah, it's still configured in the device, in the printer properly. Okay, so slice plate. How close are these to each other? Ooh, baby, they're like one wall line away. I'm gonna have to be careful not to melt into the thread channel there. Okay, well, again, we can tweak it a later time. You know what? Maybe we print with the PLA Bamboo Basic, just because we don't really need. I'm trying to use up all of this crap anyway. Alright. It'll take 15 minutes. Okay. Because we gotta level the printer. Did I peel the test track off? Yes, I did. Right. The extruder prime line. Okay. It's going. We'll turn off the calipers, and we're just gonna chill here maybe for a little bit. 53. Yeah. Oh, did I forget to turn my webcam back on? Oops. Sorry. Alright. Okie doke. Okay, that should be a thing. Okay, that'll go there. Kitty. Sorry, I'm just trying to test fit some things in here. I'm gonna figure out, so if the switch goes there, we can put the battery there. So before I sign off tonight, we're gonna drive this around. We're so tantalizingly close. I want this to move before we're done tonight. So on that note, I need to remove the drive motors from here. I need to swap these out for the motors that we have on the table. So let me do that. Let's do that right now. While we're waiting on the printer to print stuff, we'll remount the switch and get these motors swapped out. Okay, let me go grab the necessary tools. Okay, out the tools. Tools acquired. All right, so we need to start with the webcam to be turned on. We need to actually, yeah. Before I do this, let me Let me set my camera back up here, the desk cam. So y'all can actually watch what the hell I'm doing. I'm gonna set this back up. Switch over to the droid cam. I gotta change all the freaking, whether it's inverted or not again. Alright, this looks really weird on the phone screen, but should look right for you guys. Yes, it does. Okay. Alright, I got all the stuff I need. Yes. Okay. 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 Stuff here. Do the motors. Alright. So, first thing that we need to do here is find the metric ones. Pretty sure it's this one. That's one smaller. I'm gonna pull the wheels off. It's fine. Do that. Do that. Ow. Do that. Wheels slide off. And here's kind of these didn't quite adapt perfectly to the original chassis. So I have these little spacers and a couple of other adapter pieces that I made last year for this. So we'll take those out, and then we have to switch from Allen to this. To Phillips, right? Alright. Do that. Take the motor. Then we're going to have to take the adapter plates that I made for them out. And we do that with another size of bolt. And again, these adapters that I made here are just to adapt these brushless gear motors to this chassis. And the thing is that these brushless gear motors actually use the current standard for how or I should say, forget current standard. These brushless gear motors actually respect the standard for these 37 millimeter gear motors. The ones that were in this robot actually didn't respect the standard. That's why these adapter plates are even necessary. This robot was actually designed, this chassis was designed around non-standard 37 millimeter gear motors. So this plate adapts the non-standard gear motor adapts a standard gear motor to the non-standard hole pattern that's in this thing. Make sure these are aligned, right? Yeah, oh, there we go. Nice, seize it. There we go. Alright, there we go. One motor down. Place the other motor. Same story, you need to adapt the plate. I didn't quite get them out all the way. There we go.
again, we're switching from, what do you call it? 600 to 200 RPM gear motors, just because otherwise the thing would be too fast. Or it'd either be too fast or it wouldn't have enough torque. You know, I mean, even if it did have enough torque, it would be too fast. If but it might have very well not had enough torque. Alrighty, so we got those in. This in. Trouble with this, almost, but there we go, there it is. There it is. No, almost, there we go. Got one in. Okay. A little bit of gap there, a little bit of gap there. Alright, that looks good. Put these on. Spacer shafts on. The Allen keys back. Righty tighty, right? Alright. Okay, there we go. All right. Are they playing with the printer poop? The kittens are playing with the printer poop. That's funny. Okay, there we go. So we got the two motors installed. Easy to turn, perfect. Got this, got the two JST headers. All right, so let's put these two motors to the side. And then put away some of these Allen wrenches. We're still gonna need them out because we got the other ones to deal with. Let's put these away. Okay. All right. What now? Okay, we're gonna put the switch back in. That's right. Get our little flathead bit again. Take these out. Take this out. Board that we're crafting. All right. Put this back together. Where is this supposed to be? Don't break the new board. Where is this supposed to even go? I don't even know. Fingers, ow. Alright. So we put the slip ring in here to keep the switch from turning, right? I put the washer on. Has to go in that channel. Okay. Then we put the bolt on, right? So that's supposed to work, right? I think, maybe? My best guess. Yeah. That's my best guess. Okay, there we go. There. Okay, cool. We got our little thing here. We're gonna be able to tap some of this anyway. Okay. So we're just waiting for the thing to come off the printer, and we're gonna wind up our little multimeter here for a second. You know. Hi, kitten. There we go. It's back. All right. Hopefully that didn't. Hopefully that blackness wasn't too long. I guess I'll see in the VOD. But okay, we're gonna heat. Well, because we're using threaded inserts, we're gonna check to see that the iron is it's generally cooled off. So we'll swap the head for a different. Sorry about the shaking camera. We'll swap the head for a different tip. Start the heat up process of the iron. Well, actually, we need to reduce the temperature of the iron to about 400 degrees Fahrenheit. Anyway, 400 degrees freedom. Because we're going to put the threaded insert into the 3D print, which just finished. Okay. Grab the printed part. All right. Grab my M2 fasteners here. Oh, I lost one. There we go. Okay. Coming back over. All right. Oh, look at how cute this thing is. All right. All right. So let's move the robot chassis to the side for just a second. And I'm going to grab the M3 threaded inserts. Put these in here. Put these in here. And then we're gonna just push them in. Okay, it's 1. It's 2. Oh, it's not fully in there yet. That's 1, that's 2. Perfect. Okay. Perfection. Okay, cool. Pull the iron back off. Nice. Okay, so now what we need to do is take some of these longer M2 fasteners I mentioned that I had. So that's 18 millimeter. I think these are 14 millimeter. Okay, well, we'll find out. Take a few of these. See if they actually still make it through. We need the longer ones. These actually might be 12s. Okay. Oh, yeah, there we go. Do that. And okay, cool. So they still go through, which is perfect. Didn't destroy the channels with the threaded inserts. And so what we're going to do is we're going to check the alignment, which is perfect. Take these and put it through. Take this, put it through. Alrighty. And then now, like, how many of these did it take? Well, it didn't take 2 rows. It took, but we were good to give it the clearance. Let's get another nut. All right. So, take this. Thread that on. Take this. We'll thread that on. Right. Put these away. And then put those away. And we're going to need 2 shorter ones. The shortest ones we got, which is 6 millimeter ones. I believe they are. Oh no, we need M3. That's right. We made these standoffs M3, not M2. So, or sorry, the threaded inserts. Inserts are lizard. Are we need to get the short M3 screws. Which are here somewhere. Here somewhere. Where did I put the shorties? By 12. There they are. I need to buy more 3x10. Running low on those. Ooh. Yeah. Alright, I need 2 of these. Okay, now we can actually mount this thing. Alright, so let's make sure we got each cable correct. So this is the left motor. So that'll be this one. Let's not destroy a freaking connector again. Yeah, what is wrong with this? Okay. Alright, come on. What are you? feel right. Doesn't feel right. There we go. Nope, very much doesn't feel right. All right, come on, come on. What's going on? There we go. Nope. One of them got fucked. Or tried to get fucked. There's the white one. The white one is trying to get away. What is going on, man? Why are these so why are these so freaking busted? Why are those so freaking busted, man? I don't understand. Come off it, man. Just work. Oh, hey, at least it wasn't crushed. It was just knocked out of alignment. Alright. Not a repeat of the first one, but not that far off. Oh, come on. There we go. Sort of. That one's being a drama queen again. Of course it is. Of course there's a problem. Right. Why is it a problem? What is wrong with this thing? What's bent? What's not right? What if we open the connector up a little bit? Let's try that. Also, the kind of connectors have things a little damaged now because of this whole adventure. Okay. Okay. Let's try this again. There we go. It went in. Nice. Now for the other one. Perfect. All right. Nice. All right. Oh. And now we're gonna wire it up. Oops. All right, that's in there. Wire that one up. That's in there. That's in there. All right. Perfect. Perfect. Almost perfect. Getting there. Almost perfect. What is wrong now? What happened? There we go. Almost. Please, for the love of God, don't tell me that those are colliding with the motors. I swear if you tell me that those connectors are colliding with the motors, I'm gonna cry. No, they're not colliding with the motors. They are. might be too tall. I might need to lower the mounting point of the PCB. Yeah, that's it. That is what's happening. Okay. Let me just make sure that some of these are aligned better. Okay. The tolerances are non-freaking existent. Okay, cool. Actually, more or less went in. It'll be a little persuasive anyway. Okay, so cool. Now we need, which one of the? I think I need the black one. Yeah. Yep, that's what I needed. Okay. What I needed. Perfect. All right. We got a board mounted. Wow, we've got a board mounted. Look at that. We're gonna throw that up through there. And look at, we've got a board mounted. And so what we're gonna do is we're gonna make sure that the power leads aren't shorted. And then we're gonna try to drive it around. Power leads are not shorted. Good. Okay, so we're gonna take battery. And we're gonna, the battery, I believe I'm gonna tuck the battery under here eventually, but maybe after we're done debugging things, you know. It's definitely a future thing. But we'll do for now. We'll have the balance lead go through there. And we're gonna turn off the robot. We're gonna connect that. Flip the thing over. Just laugh at the attempt at holding the XT60 connector to the battery. Get another piece of tape for that. All right. All right, so we're gonna test this little boy, this little guy. We're gonna power this up and pray no fire. Gonna put this on the floor. And I'm gonna take the camera off the mount. I'm gonna try to unmirror, uninvert, and do all that unconfigure. There we go. Left side, right side. Perfect. Okay. So obviously that's over there. We're going to spin up the controller again. Okay, we're connected. We go back to Visual Studio Code, bring up the control tool. Oh my freaking God, it works. Well, it worked for 5 seconds until the controller disconnected from my desktop having oh god. Let me save the battery. Okay. You know, let's what do I do about the battery? I don't know. What do I do about the battery? Let's put some tape down. Hold on. I'm gonna do the most. Hey, baby, no, don't eat the wire. Don't eat the wire. You're not allowed to eat the wire. Okay, sorry for the black. Sorry for the black screen. Trying to tape the battery down. Okay. I've taped the battery down. Okay. Battery is more secure than it was. Okay. Still not very secure, but. The controls are so laggy because the lack of Bluetooth antennas. Okay. Whee! The stinger lives again. The stinger lives again. Okay. Alrighty. It's been, I don't even know how many years it's been since I actually had this thing driving around, but it's moving, and next video I guess we'll be finishing up the LiDAR circuit. I might actually just do this on Thursday just to make sure that we can actually get it going. But anyway, let me switch back to the desk cam. Oh, there we go. Sorry. Gotta mute the audio that I'm not using. Okay, so there we have it. We've got the dang thing driving around. I mean, let me. Oh well, it's now it's not moving. There it goes. All right, again, cats ate the Bluetooth antenna. I should probably end the stream before I just play around with it, right? Yeah, okay. So, I'm going to bring it back over to where I am. Alrighty. So, today we in a lot of hours, so yeah, in a little over, in 5 hours, I guess, it took us, we
we put together a board but I mean, baby, don't do that. Okay. In not so many hours, in 5 hours it took us. We put together the schematic for the PCB, and we managed to get the motor control components of it soldered down, along with the Pico and the power components. And we got it driving around under remote control. And again, this code that we're using is me hacking up the balancer robots code from a few months ago. Again, it's running. So I'll probably. I don't know if I'm going to be free Thursday, but I don't know what I'm doing Thursday. But if I'm free Thursday night, what I'll do is I'll host another little stream, and we'll finish the lidar soldering. But starting Tuesday anyway, we'll start working on software explicitly. So if I have enough time to do the stream for the rest of the soldering, I'll do the stream. If not, then I won't, but I'll solder off camera. Just because, I mean, heck, I'm looking at this like, yeah, there's only a couple of... Everybody who came in to watch me solder has left, so, yeah, it's fine. No worries, not a problem. It's not exactly the most interesting thing to watch, right? I'm far better at narrating code because I can sit there and look at it. It's kind of hard to be like, I got a soldering iron. But anyway, we still got to finish the LiDAR drive circuit, and we got to finish adding the IMU. But other than that, the hardware's almost done. And yeah, and so that's what we're gonna leave it for tonight. And I'm gonna probably play around with this for another hour. I'm gonna enjoy driving around because I have not had this chassis like moving in ages. But anyway, so this is perfect. Thank you all for watching. If you're watching in the future, again, thank you for sitting through this. It's 5 hours. But yeah, so we have the thing moving. We'll also finish up some more 3D. There's a couple more brackets to 3D print. But yeah, so actually, yeah. So sorry. So I take back what I was saying about software. Next stream will be, or sorry, if I have enough time to do Thursday, I will, and that'll be the rest of the soldering. And then Tuesday we're gonna do the 3D printing. We're gonna do 3D modeling and 3D printing to hold the LiDAR and the Pi on top. And actually, before I go, for tonight anyway, okay, before I go, let's test powering up the Pi. Let me turn off the camera for a second, so you don't see me spinning around. Yeah, so let's actually test the Pi. We should be able to do that. So the robot is still on. We're going to turn it off. Turn the camera back on. Still off. So we should be able to, if we're looking at this, connect this little connector. That'll go into here. So it goes into there. We can see the ribbon cable, coming off of the Pico there. That's going to come up this access thing right here. Bring that up, right? So this brings up, and we got the USB-C connector sticking out of the top of the robot, right? Now the battery is really trying to run away now. You're not going anywhere, battery. Alright, are you securing the battery? It is definitely trying to go somewhere. Okay, so well, if we didn't blow up the Pico, clearly the voltage is fine. Watch me fry another Pi. Okay, that's that. Alright, so how am I supposed to freaking do this? Okay. I wanted the connector sticking out backwards, so we're going to do this way. Okay, so we've got... Sorry. We have got our Raspberry Pi sitting on top. We're going to look at the power connector, the power light on the front, and see what happens, right? So if I flip, hopefully no fire, but if I flip the switch, the Pi is turning on. Look at that. And I got power. I don't got activity on the NVMe. But again, we're powering. We're clearly. Oh, and it's blinking. Oh, it's blinking. Okay, the Pi's coming up. And here, let's see. Let me bring up a terminal window. This Pi should be pi5.local, right? I think. Oh, I guess I have to do SSH Pi. That means it's there. Xturn 256 color, SSH Pi5. The Xturn 256 color is just because of a clash between Alacrity and my terminal emulator here. That the Ubuntu, which is running on this Pi right now, doesn't know what to do with Alacrity. So there it is. LSUSB. Okay, so we don't see the Pi, but what we can do is wow, the freaking this has to actually be. I wonder what the algorithm's going to do this, but okay, so we want to do sudo raspi raspi conv. Actually, we don't want to do that. We want to do sudo-i. And then we want to do boot firmware. And then if we look at config.txt, what we can actually do is there's this little kind of hacky thing that we can install. So yeah, enable USB 2 outputs on the I/O board, assuming that your CM4 is plugged into the board. However, what we can do is if we put that into all instead of just CM. Actually, we'll leave the CM4 thing where it is. But if we actually do that DT overlay. Oh, wow. Hitting the wrong key. DT overlay equals DWC2 DR mode equals host. And, you know, watch me not be able to type. So we're going to say enable USB 2 on the power connector. Okay. And then if we reboot, we should be able to see the Pi, the Pico, as a USB device on this Pi. Just gotta wait for it to come back up. But yeah, I mean, again, not super great, but you know, here we'll build the right mounting jigs for everything next week. But we are running the Pi off of this battery, which is coming through this ribbon cable, you know, into the Pi, right? And so let's try connecting. Let's see if I don't know how fast Ubuntu reboots on. Here we go. We do LSUSB, Raspberry Pi Pico, and we can see the Pico over the power connector on the Pi 5. And this also works on I know this also works on a Pi 4 because I've tested this on a Pi 4. I don't know about the other Pis, but basically, if you've ever seen, if you've ever used the compute module, the only actual USB interface on the Pi's CPU is a USB 2 interface. And the way that the Pi 4 gets its USB ports is there's a VIA, VIA, it's a VT805 USB controller, and it provides all the ports, but it's PCI Express attached on the Pi 4. That's what uses that one PCIe lane. And so you get two USB 2 ports and two USB 3 ports, but they're all sharing a 5, gigatransfer, so all the USB has to share 500 megabytes a second. And the same thing's on the Pi 5, but you have that RP1 chip, right, that has the two individual USB controllers plus the two USB 2 controllers plus everything else, but that's running over a Gen 2X4 interface. So there's a lot more. There's 2 gigabytes per second of bandwidth for all that stuff. But with the Pi 5 here, so either way, like if you had the Pi 4, you only had the USB 2 interface off the CPU, and on the CM4 that was broken out to the connector. That's how you would program it. How you program the eMMC is you'd run a little bootloader that would make it a flash drive essentially. but that you could then write to. But with the Pi 5, I mean, with the Pi 4 and the Pi 5, the normal sized Pi, those USB lanes actually go to the power connector. And, it's not a proper, device upstream, downstream negotiating thing, but it does, the lanes are there. So you can do this horrible, like something like this horrible contraption where you can, use a Pi Pico. You can backfeed a 5-volt regulator over the V-bus pin, that it comes back out of the micro USB connector. You could run a Pi 5 off of a Pico, backfeeding power. You wouldn't want to plug this into your computer at this point, but because you really don't want to worry about what happens if you stick power into the USB port. But yeah, so we've got, and if do I have PicoCom installed? Probably not. Okay, apt install PicoCom. I don't know what it'll take to reboot the... Well, actually, I do have USB debug installed on here, so if I bring in Pico tool, I can probably reset the Pico over the bus here. So apt search Pico tool. I don't know if it's up in apt. I don't know if they... No, they didn't. But let's grab Pico tool. Raspberry Pi Pico tool. Yeah, okay, so let's do git clone Pico tool. I don't even know if I have a compiler installed. I don't. Sudo apt install build essential. Clearly we had git. We'll probably need cmake, because Raspberry Pi likes cmake. I like cmake, but cmake... I wonder if Vim's installed. Okay. Okie doke. Installing. Why do we have to install AOM? Oh well, whatever. I don't care. Okay. Doing this. So we've got... Oh wow, I got 2 concurrent viewers. Okay. So yeah, right now we are backfeeding power out of a Pi Pico into a Raspberry Pi 5 to power it. It's this horrible contraption where if you look closely, you can see there's a ribbon cable coming from a Pi Pico in the bottom here. I'm sorry. In the Pi Pico, and it's backfeeding up into the Pi. And what we're doing is we're looking at we added this hack to... Oh, it's not a hack. It's the supported feature. Boot firmware config.txt. You can see that we added this device overlay, which enables the USB ports, the USB lanes that go to the power connector on the Pi 5. Anyway, so we can see the Pico on LSUSB. We can go to Pico tool, and then we'll do cmake I probably haven't installed Ninja. Yeah, apt install Ninja build. Okay. Scanning Linux images. Okay. When we're gonna come to cmake Ninja cmake build type release b build dot Pico SD. I really have to get the freaking SDK. Okay. Okay. Pico tool. Okay. What I need Pico RM RF build CMake Pico SDK path equals home slash Pico SDK. Oh dear. libusb. Oh geez. Okay. Sudo. Well, that's. I mean, why would it be installed by default? That wouldn't make sense. It really actually wouldn't. There we go. If compilers aren't installed by default, why would libusb dev be installed? It's fine. And then we need Pico SDK. Probably do a git submodule update init for this. Oh, sorry. Update init recursive. Okay. George Robotics CY43. Interesting. Cutie. Cutie. Yeah. I'm just waiting for it to clone some stuff. How long this is going to take? Probably one of the best Wi-Fi connection in here for this thing. What this pulsating? Yeah, anyway. And USB. Oh, it is making progress. Oh, there we go. Come on, it's almost there. Embed framework. Okie doke. Almost. Maybe. We'll see. Okay, cool. Actually, another one that we need to look for, app searched EEPROM. Alright, we want to install Raspberry Pi EEPROM. Oh, we have it. RPI EEPROM power override is another thing. How to power the Pi without the official power supply. There's a max current enabled, but we can also override PSU max current in the EEPROM config. So we'll just do sudo RPI EEPROM config. Nope, wait, that didn't set anything. How do we do that? Let's see. Oh, edit, I guess. There we go, PSU max current 5,000. And so what this will do is, what do you call it? The whole needing USB PD with the special 5.1 volt 5 amp profile. Otherwise you end up with warnings about not being able to pull enough power. Well, that fixes that. Well, fixes. I mean, realistically, you should use a PD supply that will actually tell you that you can pull 5 volts. 5 amps. But that also works. Now it'll just suck 5 amps and assume that it's available, which is probably a bad thing, but you know it works in this case because there's no PD over a micro USB cable. Okay, and so updating bootloader could take a minute. Don't disconnect until complete. Update successful. Perfect. But now we can go to Pico tool, RM build, and then we're gonna do control R Pico SDK path build. No libUSB. What the? I installed it though. Apt search libUSB. Wonder which version of libUSB it's using. libUSB dev. Oh, is the old 0.1.12. libUSB 1.0.0. There we go. That's probably what we want. Habibi, Habibi. No, stay over there. Boop. Okay. Cool. And found libUSB. Perfect. And we don't have package config, so we ought to install that too. That's just from build tooling, you know, Linux build tooling. But yes. Build, and we're gonna do our Pico SDK path. Okay, nice. So now we do Ninja C build. Cool. Actually compiling on the Raspberry Pi 5. It's not a slouch. Pico tool. Alrighty, almost there, theoretically. Bin tool. Just gotta get to the final link. Link! It's probably running slower because it's expecting a power limit. But it's so far so good. Make sure it hasn't crashed or anything. Yeah, we're good. Yeah, it's just compiling a thing. Doing a link. There we go. Alright, so Pico tool. Build / Pico tool info. Hello, there we go. Address, bus one address super Pico tool. Maybe try sudo, which probably don't have dial out. Consider F to force a reboot in order to run this command. Pico tool info. Oh, aha! The robot's turning because that stupid thing where the motors do the stupid shit. If you remove their connection, so the robot's slowly turning. There we go. Okay, but we are looking at a Pi Pico. So we look at the so if we do a Pico reboot, and we do a Pico com dash d dev ttyacm 0 and then b1152. Man, okay, PicoCom. Oh, I did this bad. PicoCom 5200 dev ttyacm 0. There we go. But there's nothing being, sent to the terminal at the moment, so we're gonna do a reboot and then a PicoCom. See, there we go. Wi-Fi joining. Link fail. Joining. Link up. PicoBot local. Okay, there we go. So we see the printfs coming out of the Pi Pico over USB again into the freaking power port of the Pi. And that's how we're gonna have the Pi talk to the robot. Yeah, so there we go. Pi Pico, Pi 5 with a Pi Pico. was talking to the robot chassis, and so but apparently. Okay, sorry, trying to fill airtime with my voice. So what we'll do is on before next week, I'm going to finish the soldering. If anybody's interested, I'm going to try to host a Thursday night stream for doing the soldering. If I am busy or have something else I need to do, I won't do it Thursday night. But at any rate, I'll finish the soldering before Tuesday, so that we can drive the lighter. And then Tuesday, we'll dive into FreeCAD full send and model all of the stuff that we need to bolt to this chassis in order to mount the Pi, mount the battery, mount the LiDAR, and then we'll have our frame. And so that's what we'll do. So yeah, maybe join me Thursday. I'll put a post out probably day of if I figure out that I have the time. But other than that, check back in on Tuesday, and we'll do the 3D modeling for this stuff and fire it up on the printer. But hope to see y'all there. So thanks for watching. If you're watching this in the future, thank you. Also, thank you for not ending when I said I was ending 20 minutes, maybe more than 20 minutes ago. But either way, hopefully you found this interesting. So join me again for another stream. Maybe Thursday, but definitely Tuesday. So have a good evening or morning, because it's past midnight now. It's now Wednesday. All right. Good night.